the Management Science and Engineering Department at Stanford University. He has worked in a number of areas, most famously on social networks, social choice, market design. He was a research fellow and technical advisor very early on when Twitter started, and he is behind the early algorithms for personalization and monetization at Twitter. His work on auctions, specifically sponsored search auctions for Google, has recently received the Desktop Time Award by ACM, and he has been involved in important works. For instance, the Stanford participatory budget is coming out of Ashish's group. So welcome to this workshop, and I hand it over.
Thanks for the intro, and thanks, Sandeep, for the invitation and for the entire organization. This talk is going to cover a lot of ground. A lot of terms are going to be unfamiliar because there's a bunch of optimization, but also a bunch of just finance stuff. So I'm not wedded to finishing my talk, so please stop me as often as you like for questions. Even the technical stuff often has somewhat simple explanations. And there's one part of the talk I really want to finish, but I discussed with the organizer that he's going to give me like a 10-minute warning. So that one part I'm going to definitely get to. So decentralized finance. Sorry, thank you again, everyone. That didn't get recorded. Thank you. So decentralized finance is, what is decentralized finance? Here's an aspirational definition of DeFi. Okay? The reality doesn't actually necessarily match what happens on the ground, but decentralized finance, or DeFi, is a financial system where any agent can create a new market, an exchange, or a financial instrument, and other agents can participate in this new market or freely trade this instrument. Okay? And at first glance, this just sounds like finance, right? It doesn't sound like decentralized finance. The decentralized part comes in because an agent can create this new market, exchange, or instrument without regulatory hurdles. Okay? To get a new exchange approved in India, it's probably like a 3-decade process if it actually happens. In the US also, it's a multi-decade process. Okay? So it's not just something, if you want to create a new market, it's not just, you can't just get up one day and say, I want to make the Chicago Mercantile Exchange. But in DeFi, you can. Okay? And this system has to have unambiguous definition of the rules of the market. Okay? Even big exchanges are somewhat ambiguous, and there's disputes all the time which then have to be resolved by the courts or by regulators. But in DeFi, the goal is to have unambiguous definition of the rules of the market. And the agents which participate under a guarantee that the rules of the market will be rigorously followed, okay? Without fear of censorship or lockouts. Okay? And you can immediately see a tension. If there's no regulatory hurdle, there's no one regulating this exchange, how would an agent be guaranteed that the rules are rigorously followed, right? Exactly followed, precisely. Okay? And how will the rules be rigorous? Okay? And so why is this interesting and why now? Is because DeFi can be implemented using smart contracts on permissionless blockchains. Okay? That's why sort of DeFi and blockchains have become so intertwined. Okay? Because anyone can write a smart contract. A smart contract is a piece of code that clearly specifies who can update the state of the contract and under what conditions. Okay? For example, if a piece of a collateralized asset belongs to agent A, taken my home, I've divided into 10 chunks, okay? And I put each of these chunks as a token, which is on this on some exchange. Okay? Then if you own one of those pieces, you can split it, you can combine with other pieces of the same asset, or you can transfer to another agent in return for some specified amount of cryptocurrency. Okay? So that would be that's not the only smart contract, but that's an example of a smart contract. Okay? And if you run the smart contract, then you're guaranteed that these rules are rigorously followed. Only one person owns a piece of the asset and they can freely sell it. Correct execution of this can be cryptographically guaranteed, verified, or proven depending on what kind of framework you want to be in. You want guarantees, verification, or the ability to prove it. Okay? And permissionless blockchains is a decentralized collection of ledgers and execution engines. Okay? Think of it like a computer, a small execution environment with a small database. Okay? or a small SQL table where anyone can run a ledger. So anyone can, it's permissionless. Anyone can come and say, okay, I am also going to make a copy of this ledger in this engine. Okay? And a consensus algorithm ensures that these ledgers and these execution engines move in lockstep. Okay? So anyone can make a ledger, but then to write to that ledger, you have to have consensus among all the nodes. Okay? That's a permissionless blockchain. Okay? And because these two things work so well together, that's the reason why DeFi has become possible, why you can make these complex markets without any regulatory hurdle, and while still making sure that their rules are rigorously followed. Once again, if this language is too vague, please feel free to interrupt me to clarify it. If you want examples, please feel free to clarify me. If you have moral objections, please feel free to voice them. Not everybody agrees that blockchains are a positive thing or smart contracts are a positive thing, and it's a fine opinion to have and it's a fine opinion to voice. And or if you have any specific objections, I'm happy to answer them to the best of my ability. Okay? So here's an example of DeFi. The simplest one is cryptocurrency, a token issued on a blockchain that can become a repository of economic value or a means of exchange, okay? Like Bitcoin. You can have a stable coin. A stable coin is an asset which is pegged one-to-one to a basket of real-world currencies. Okay? It's pegged one-to-one. What does it mean to be pegged one-to-one? It has to either be backed by reserves, and these reserves then generally have to be audited and guaranteed off-chain, okay, not on the blockchain itself, or algorithmically, which can break. So these things are not perfect in some ways. You can have collateralized assets. You can have multi-currency exchanges, escrow, programmable payments. So for example, someone delivers something to you and you do cash on demand, but that cash on demand is like programmable. As soon as the courier takes a picture of the package at your front door, your bank account, the money sort of goes to the seller. Okay?
So just a clarification. So is your position that this is a closed system because the stablecoin actually requires you to go outside of the DeFi?
Stablecoins break this idea of a closed system. They are like we're going to sort of try to recover that idea a little bit later. But yes, stablecoins by themselves are a fine DeFi primitive, but they don't make any sense unless you have this connection to something outside. Okay. And so there's some, yeah? The assets could be on the chain. So for example, what you could do is you could actually put a stock certificate or a deed on the blockchain, but then you would have to have someone else which guarantees that they're holding it in reserve. So yeah, so that they also break this. It's not, so this abstraction is like not perfect. So that was like an aspirational definition, and in the real world, you would have some break in the stylized model. Okay? Here are some caveats in an Indian context. They're generally in any context, okay? But definitely in an Indian context. For DeFi players, if you want to do DeFi in India, say you are Coinbase and you want to make a wallet, or you are Tether and you want to use a stable coin, there's some regulatory ambiguity under RBI. Okay? There's uneven enforcement. And there's a possibility, a suspicion that this ambiguity is deliberate to keep people on their toes and to be able to sort of enforce it if something goes wrong. And so there's some deliberate regulatory uncertainty. Yeah? I mean, I don't know whether it's deliberate. The fact this ambiguity is clear. Whether it's deliberate or not is what people suspect. Yeah? For the consumer, there's a lot of fraud and misrepresentation. Okay? A lot of unsavory behavior happens on blockchains. The exchange failures, like a algorithmic stable coin failed and there was no recourse. Okay? Even the ones which are backed by reserves, these reserves are sometimes opaque. Okay? They're self-certified. For the government, this creates law enforcement blind spots for drug trade, money laundering, cross-border crime, terrorism financing. The tax compliance and attribution challenges. There's a potential breakdown of currency controls. For example, the Indian rupee is not fully convertible. But what does it mean for a currency not to be fully convertible if there's a stable coin in that currency that's just trading on Ethereum? Yeah. So India's regulatory stance is a guarded no to cryptocurrencies. Okay? By guarded, no, in the sense like it's a soft no. There's no regulation, but generally there's enough enforcement, somewhat uneven, that big players like Coinbase take it as a no. A guarded, yes, to programmable payments. For example, the head of NPCI has issued a statement saying that they do want to have programmable payments. They do want to have some kind of a cryptocurrency kind of architecture which is regulated and controlled. Okay? And so the architectural question, given this regulatory stance, is that permissionless blockchains is still the right architecture to deliver DeFi in an Indian context. Okay? And we'll revisit this question at the end. So like I said, this talk covers a lot of ground, and hopefully this gives you some like grounding of what the high level issues are. Now the high level issues are like, they're fun to talk about, but there's not that much technical meat to them. So I also want to give you a flavor of things which are more explore like the kind of optimization problems, the market design problems that underlie this. So I'm going to take a break from this, this chain of thought. We're going to do like a straight we're going to point out some market design / optimization issues in DeFi. Okay? Once again, at the high level, if you want to stop me, stop me. And in the end, we'll come and revisit this architectural question. And I have a concrete proposal that I would love to get everyone's feedback, advice, collaboration, help on. Any questions? So the outline of the technical part, we're going to discuss two ideas in exchange design with newfound popularity. We're going to discuss how would we combine these two ideas. Okay? And we have, for both ideas, we have some preliminary work, but we also have work on combining them. And somehow I want to give you a flavor of both these things. Okay? And the goal is to map out the design space. There's no dominant design. And so, but just understanding the vocabulary, just seeing the kind of issues that arise, if you actually start to take this DeFi idea seriously, and design new market primitives on top. So here's a very simple exchange model. Yeah. Imagine that users trade indivisible fungible assets through limit orders. Yeah. And this is different from the kind of trades that happen currently. Okay. Currently, most exchanges have a single denominator in a single currency. So if you can go to an exchange and you can say, I want to sell Infosys for at least this many rupees. Okay. So but this rupee part is fixed, or the dollar part is fixed. These exchanges are denominated in a single currency. But now we are thinking of an exchange where you have these assets, then you can trade any asset for any asset. Okay. So you can issue an order saying, I want to buy 2 units of, I want to buy 2 microbits of Bitcoin, and I want to pay at most 20 rupees. Okay. And so batch exchange is a new kind of idea that's emerging, which is execute batches of these trades all at once. Okay. And so the input is a set of limit orders, and these limit orders on this exchange are between any 2 assets. Okay. It could be like, I want to sell Infosys stock, and in return I want Wipro stock. Yeah. And what these batch exchanges will do is they'll then compute prices. Okay. These prices themselves may not be super meaningful, because what matters is price quotient. Okay. What matters is the ratio of the price to Infosys to Wipro. Then you trade these in batches at these price quotients. Okay. The quotients are meaningless, but when you trade, there's no pairwise matching. Yeah? You can have a market clear without saying exactly who is selling to who. Yeah? As long as the total amount sold in these price quotients of every stock versus the total amount bought nets out to 0, okay? There's no reason to assign pairwise matching. Okay? So it's an exchange which breaks this idea that one person is selling one asset at some price to another person. It's
within each batch, the order should be completed. Is that the point?
Within each batch, the orders, sir?
Like within each batch, there should be complete settlement.
There should be complete settlement, but not pairwise. Yeah. So it's clear, but there's no one.
Break down who gives who how much.
You might not be able to, because you might clear it along a cycle, along some complex structure. It's like it's an exchange in a traditional sense that it clears. Yeah. Yes.
But this information
Sorry? You have to have a minimum of 2 edges. Yeah. So you have to have a minimum of 2 edges. You can say more things. You can say you have to be able to decompose all the transactions into a collection of cycles. So they have to be like, even though things have to be cleared along a cycle or a collection of cycles. So whatever you have, you can show it is going to be. So there's some structure. The fact that it has to clear imposes some structure. The fact that there's some price quotients also impose some structure.
So is there any,
Yes.
So I was trying to understand, is there any specific, let's say, optimization, let's say, where the size of the cycle, like for example, if I compute the current, let's say, prices around the cycle, and when I execute, because the trades are executed one time, right?
Yeah.
So it can vary at the end of the cycle or in some way.
Yeah.
After the trades are being executed during the execution time.
Yeah.
Like this happens in currency arbitration also. I think it is a similar cycle that we are talking about.
No, that cannot happen. So what you're describing, if the market, so that's one of the conditions that these prices have to satisfy. So what these prices have to satisfy is a no arbitrage condition, that along any cycle that you're actually doing, the product, so the prices can vary as you go along the cycle, but the product of prices along any cycle that you actually use has to be exactly one. Does that make sense?
I will do a reading on that. Yep.
Okay.
How do you figure out what is a batch and what happens if there's something that cannot be matched? They're just, like, those orders are rejected.
The orders which cannot be matched get rejected. Yeah. How do you figure out what's a batch? And so this is where these things get intertwined with blockchains. Okay? For now, let's stick to a blockchain architecture. I'm going to suggest a different architecture at the end, but for now, let's stick to a blockchain architecture. By definition, in a blockchain architecture, you need to have consensus. So in this particular exchange, you will have to have multiple stages of consensus. The first stage of consensus would have to be that you have to agree what trades have been submitted. But blockchains already support consensus. So this exchange, the way it would happen is first, people agree on what things have been submitted. Okay? And they use standard consensus for that. Once they agree what has been submitted, then the batch that's under consideration is fixed. Then they run an algorithm to do this price computation. We'll have to do some work in a real system. You have to do some work to make sure that as you do this price computation, it's stable that everyone gets the same answer. And then once they get the same answer, then they come up with the series of trades. They update their internal ledger and then do another round of consensus. So, but this extra round of consensus, given that consensus happens all the time, an extra round of consensus is not a problem. Did I answer your question? So you'll have orders which might look like this. I kept like rupee out of this thing because I'll say something else about like what I think is the right architecture in India later on. And so, and then there's a pricing engine which will compute these price quotients and things will clear. Okay. And the other exchange design innovation that I want to mention is a constant function market maker. Okay. And this looks very bizarre when you first see it. Okay. And so it requires some, so even though it's one slide, it's doing a lot of work. Okay. So a constant function market maker or an automated market maker is something where you can make a market where you can trade when you do an exchange, but you're doing an exchange not with another person, but with the market itself. Okay. So generally, instead of saying I'm going to sell 5 units of something and someone else is going to buy it, I just say, okay, I have, I want to sort of, there's a market between, let's say, rupees and micro bitcoins. Micro bitcoin is like 1/1,000,000th of a bitcoin. And so you can just go to the market and you can say, okay, I want to sort of buy bitcoins worth 100 rupees, or I want to buy, sell bitcoins, 10 micro bitcoins, how do I do it? Okay? And so this market will directly satisfy your request. Okay? But when you have a market which directly satisfies your request, the question is how do you do pricing? Okay? Normally pricing in these exchanges happens because you have many orders and you find a clearing price. Okay? If you're trading directly with the exchange, how do you do price discovery? And these constant function market makers do this price discovery by declaring upfront that there's going to be a constant, there's going to be a fixed trading function. Okay? So in this particular example, we have taken the trading function to be xy equal to 10 to the power 7. Okay? And that formula is fixed. Okay? And at any given time in this market, you have some basket of assets. So let's say currently you have 10 to the power 3 micro bitcoins and 10 to the power 4 rupees. Okay? This is like roughly the price right now. So it's like roughly. And so given these, given this current state of the market, okay, so these reserves 10 to the power 3, 10 to the power 4 are the current reserves. Okay? You have that many micro bitcoins and that many rupees. Then there's a trading function f that in this case is xy equal to 10 to the power 7. Okay? And then this market accepts a trade from x comma y to x prime comma y prime. Like anyone can come and move the market from xy to x prime comma y prime, if and only if the trading function does not decrease. Okay? So what that means is, if I want to trade buy or sell on this market, I can move the market from here to here. Okay? But I cannot move the market from there to here. Okay? And then as a result, the tangent of this curve gives you implied prices. Okay? And it turns out that these markets are sort of quite popular. They're market makers who come in, anyone can come and create a market. So you can go right now and create a market in any two assets which are like legal to trade. Okay? You can put whatever initial amounts you want. You can put whatever trading function you want. Okay? If the trading functions that you put in make sense and the amounts that you put in make sense and people use your market, then you might make some money because you'll collect some fees on these trades. And if you use a trading function that's not appropriate in this case, then you're going to lose money. Okay? Yeah?
What exactly is the point of this? So you're saying that in some sense it's measuring the value of your reserves so far, right?
No. F is something that you specify.
No, but what's the equation of that? Like, is it just a number?
No, it's a function.
Yeah, like, as in, no, but you fixed it, right? It's that xy equals to something.
Yeah, so I fixed xy equal to 10 to the power 7. That's my trading function. I specified it. So I create this market. I specify xy equal to 10 to the power 7. And I establish reserves of 10 to the power 3, 10 to the power 4, which satisfies this trading function. Is your question, why am I doing it? Because, for example, if it's not micro Bitcoin, if it's Ashish coin, okay, I might have vested interest in providing liquidity for Ashish coin. Okay. So I might have some vested interest in saying, okay, I want to create this market because this market is serving some other goal for me. Okay. So for example, you might have heard that anyone can now issue a meme coin. You go and issue a meme coin, but people want to still be able to trade, and so you create this market. And on this market, you don't have to do pricing, you don't have to do price discovery, you don't have to sit around and satisfy anything. Just create this market, you put these reserves in. It's a smart contract. People can just come and automatically trade on this smart contract. As the price of this meme coin, Ashish coin moves, people are going to trade this to find the correct price on the curve. The tangent of the curve at any time gives you the price. And so it's a tool for like automated price discovery. In the process of moving from here to here, maybe there's some, I lose some money because I was mispriced. But that's the risk I take in return for the fees that I'm going to collect for people who are going to trade in this market. And that's also the risk I'm willing to take because I have additional vested interest in facilitating this market because it's my meme. It's not my micro Bitcoin, it's my Ashish meme coin.
But why is this the right way to do it?
Why is this the right way to do it? Like, why is this the right trading function? I mean, it has many advantages. You mean not this specific? Why is this entire design the right function? It may not be the right thing. So it's an example of a market that people create. Yeah? It may or may not be an optimum way of doing market making. Okay? It's clear. So this is an example of what is called an automated market maker, yeah? Where the market maker, there's no price, there's no external. The market automatically computes the prices and allows you to trade. Okay? Now, automated market makers have a lot of great uses. You can just like make them, forget them, they provide liquidity, they serve a real purpose. Now, this is a specific kind of automated market maker, which is a constant function market maker. There's a specific kind of constant function market maker which uses the product rule. And whether this specific thing is the right thing or not, I don't know. But it does serve a role. It serves this role that you can do automated price discovery, you can keep trading here. Can someone guess what the without checking on your internet or without either Googling or AIing it, can someone guess what the volume is for this particular market? There's one particular protocol, a smart contract called Uniswap, which uses a slight variant of this function. Can someone guess like the volume on this, let's say daily? Like how much money trades every day using this formula or a slight variant of this formula on this one smart contract called Uniswap? Sorry? Yeah, I think everybody is guessing very high. It's like $400 million, yeah? Which is like which considering it's a daily volume, which given like how people are surprised that this market exists or why it exists, is an astounding amount for something which, like if you ask me, I cannot like honestly say that this is the right design. I don't know. I mean, it's a design, but it does. 24-hour volume is more than $400 million on this one type of smart contract with this one basic formula. Yeah? It's now big enough that they have some variance around it. They divide into like chunks and they do like different kinds of things, but that's the original basic formula. And that market is called Uniswap. So for example, if I wanted to trade, I could move this to 10 to the power 4, 10 to the power 3 if I wanted. Okay. And when I move a market from one place to another place, I get the delta as a trader. Okay. So I'm going to describe some results that we have derived for batch exchanges, some results that we have derived for these constant function market makers. And then if there's time, I'm going to describe how you can combine these two. I mean, that's the main topic, but we might not get to it. Okay? And this is going to be sort of a little bit more of a technical description. And then we'll go back to the architectural question about if you want to do things like this, or stable coins or escrow in an Indian context, what's the right architecture for doing it. So an ideal decentralized exchange, let's say a batch exchange, would have very high performance. So for example, the top curves here are our system, which I haven't told you about. The bottom curves are existing payloads. And in like a medium contention situation where like, and let's not worry about like what contention is for a second. You can do around like 100,000 transactions per second, which is actually not that much, okay, for a financial system. And so you want computational performance to be very high. You also want economic performance to be very high. Like any exchange, you want to do efficient liquidity usage, which means like you want to make as many trades as possible. That's how you can think of it. You want to minimize things like front running, which is like a form of momentum trading, and you want it to be like the fair open access. You want it to be clear what's happening. So a lot of decentralized exchanges today, they do sequential order book updates, and they do pairwise trading. And so sequential order book updates, they have a very low throughput, because there was this question that got asked, which was how do you decide what the batch is that you're trying to clear? You're doing sequential order book updates, and after each order book update, you have to then go and do this kind of consensus, which ends up becoming very expensive, or you have to have like complex logic to support it. And it also leads to front running, okay? Because if a sequential order book update, then if someone knows you're about to submit an order, they can front run by submitting an order, sandwiching your order before and after with another order, and they can squeeze all the spread in the market, leaving you with worse prices. Okay? But then also it's just hard to, you're not going to have, let's say, let's forget about Bitcoin and rupees for a second. Let's imagine that these two cryptocurrencies, which are also heavily used, but maybe not as common as Ethereum or Bitcoin, and you want to trade, issue a trade from one to the other. Okay? The way you would do this trade is you would have to go via a sequence of trades. If there's not enough liquidity between this pair, okay? So if there's not enough people who want to directly trade Naira and Sol at any given time to be able to have to run an exchange directly between Naira and Sol, you have to convert this to some currency, that to some currency, that to some currency. You have to find this path. Okay? Now each of these is going to be like one step on in a blockchain order book clearing. These prices are changing all the time, the availability is changing. Okay? And even between Naira and USD, there may not be like a fixed price. It might be like lots of different, to go from here to here, there are many different ways of doing it. There are many different orders you can trade against. Okay? So the whole thing becomes a big mess. If you're trying to trade two currencies which don't have a high enough liquidity between them to run like a direct continuous double auction. Okay? So these continuous double auctions, which is how these exchanges are generally run, rely on having a lot of liquidity. Does that make sense? And so what we have is we have developed this system which is backed by some sound theory for doing this kind of batch trading, taking both economic and computational performance into account. The system, it computes a valuation PA for each asset given a block, okay, and that's just like I said. Exchanges from A to B happen at exchange rate PA over PB using these price quotients, and offers trade with the market only if the limit price is less than or equal to PA over PB. Okay? Then they trade at this price, otherwise they don't trade. Okay? And there's a theorem going all the way to Arrow and DeBrew which says that there exists a unique set of valuations that clear the market. So these these things can, at least these market clearing prices exist, okay? And they're unique. So you don't really have to worry about what if one person uses one algorithm and another node uses another algorithm. But just because they are unique does not mean that you can efficiently find them. Okay? Under some restrictions, you can show that you can compute them in polynomial time. I'm not going to dwell on exactly what those restrictions are. I'm going to just focus on the polynomial time algorithms. Okay? Okay? And computationally, so economically, this sort of gives you efficient liquidity usage, eliminates in-batch front running. Okay? Because the prices within a batch are fixed, so you cannot front run within a batch because everybody gets the same price within the batch. So you can't do a sandwich attack on a trade within a batch to extract value. And then you get computational performance by doing scalability from parallelism by using commutativity. And this is like it's like a more of a systems thing. What happens is once you decide the prices, once you have computed the prices, then different orders commute. Okay? Once you have decided what prices you're going to have, then offers trade with the market only if limit prices less than or equal to P over PB. Then I can look at any limit order and you can know whether this limit order is going to get fulfilled or not without having to look at any other limit order. Which means that I can then clear these ones which are going to actually execute in parallel. And that's a big deal because these things are not like just currencies where you're going to just go and modify a database. Because these are cryptographic currencies, to actually sell one asset, to exchange one asset for another asset requires you to go and do some complex cryptographic bookkeeping, which is very expensive. So the fact that you can, once you have these prices, different orders commute with each other. Yeah? That means that you can actually use parallelism to speed them up quite a bit. Yes?
How do you compute PA by this PA by PB ratio without having these orders? Isn't it
No, you have all the orders, you compute it. The computation is not parallelizable, but this is what, yeah, yes. In this domain, being optimization people, we look at this complex problem, we assume the computation is going to be the bottleneck. In this particular case, what happens is the computation does take time, and you have to be careful about it. But the real bottleneck happens when you have this, you have a batch of, let's say, 10,000, 100,000 orders. You want to execute that batch. For each pair, each asset, you have to go and decrement a ledger and update a ledger. That updating and decrementing the entry requires you to do some cryptographic bookkeeping. These things are arranged in some kind of like a tree of some kind of a cryptographic tree. And the cryptographic bookkeeping is very expensive. So the fact that once you compute the prices, you can, then these offers, then having computed the prices, these commute, they give you a huge advantage. And that's very counterintuitive, but that's just the way these things are designed.
So there's no precedence like or an order with a better limit price may not be in the block. It is possible in the batch.
So you're saying the batch, there might be price volatility from batch to batch? Is that you can say?
Let's say that in a batch, so a batch is selected by the miner.
Yeah, yeah.
So an order with a better limit price, it is possible that it was left out of the batch.
It's possible. So you can do other kinds of attacks. So there's like a lot of scope for hanky-panky in these markets. So I said like it's minimize so what I said was at some point I think that we can eliminate in-batch front running, but you cannot eliminate other kinds of market manipulation. You can still do things like momentum trades, where you could just drive up the price. You could just do, so momentum trades are like a trading strategy. What you're describing is even more nefarious. You just leave something out. But the hope is that because it's a consensus method, it'll be hard to do it systematically. So as it turns out, for a subclass of this, a reasonable subclass of this market, we have a subclass where you can have buy orders but not sell orders, which is not a problem because this it's a multi-currency market. So selling A for B, you can convert it to buying B for A. Then people have figured out like a tractable convex program, which if you solve it is going to give you this answer. But this convex program is very hard to solve efficiently, and when you get a solution, there's always some inaccuracy which ends up killing you because you want very precise clearing guarantees. Okay? So for the first thing we can do is instead of trying to solve this convex program to great sort of precision, to 100% precision, you can solve it approximately, and then you can run a linear program which can clear the entire market by just writing balanced conditions and by imposing a fee. So if you impose a small amount of fee and then you say, okay, I can't, earlier I had this guarantee that the market exactly clears. With this fee, I'm going to say the market is allowed to approximately clear. Anything that's left after approximately clearing the market, I'm going to take it as a fee. And that allows you to solve it, take an approximate solution to the convex program and essentially round it very efficiently to a very precise solution. And this also gives you exactly which trades are going to execute and which ones are not going to execute.
Exactly. So the point is that the transaction fee acts as some regularization and then you linearize it?
Yes, so transaction fee acts as a regularization. So the transaction fee gives you like a fudge factor. So the convex program has to be very finely tuned. This clearing constraint means that the prices would have to be computed to almost an infinite precision. You can't compute prices to infinite precision, and so you can never guarantee the clearance conditions exactly. Also, it just takes a long time for it to converge to that level of accuracy. So what you can do is you can say just converge to it till you have like within 10 to the power minus 5. And then a linear program which for these fixed prices, you fix the prices. For these fixed prices, you say use a linear program to figure out what's the maximum number of trades I can do. And whatever is left as a balance, because you're not doing as many trades as possible, it'll create a small surplus, you charge that as a fee.
So you first solve the other program and then
You first solve a convex program approximately, and then you use a linear program to precisely round it.
and the approximation factor is something which you would call the transaction.
So we don't really have the approximation. So this convex program is tractable in the sense you can solve it in polynomial time. So if you want 10 to the power minus 5 accuracy, the running time will be like 1 over some function of that. So you run some kind of iteration method till you get the required accuracy, and then you round it. And so this fee is sort of what allows you to thinking as a regularizer is maybe a good way also of thinking about it. So there's one of those things where if you didn't have a fee, you'd have to have a very 100% precise clearing. So this is one of those things where you can actually justify charging a small fee because otherwise you would not be able to clear exactly. So all prior known algorithms for this had a runtime which was polynomial in the size of the batch. And you can, as it turns out, and this is sort of more like a software engineering kind of thing, you can design a Tautonement-based scheme which sort of iteratively computes these prices, where the runtime is much smaller. It's number of assets, it's square of the number of assets as opposed to the number of polynomial and the number of offers. And based on this, what we found is that it takes around 100 microseconds per iteration, around 1,000 iterations. So which means that in around 100 milliseconds, we can do this price computation. And that turns out to not be a bottleneck because with a lot of, and this is for around 10 to the power, batches of size 10 to the power 6. For batches of that, which are that big, it takes longer than 100 milliseconds to just do the bookkeeping. So so what that happens, if you do a small amount of software engineering on top of this convex programming framework, then you end up, this ends up being not the bottleneck. Once this is not the bottleneck, then you can have many CPUs in parallel doing the actual cryptographic clearing in parallel. And then because these things commute, it doesn't matter exactly how you parallelize them, which gives you a lot of design flexibility. Because these are permissionless blockchains, so it's very hard to synchronize every architecture in such a way that they have exactly the same number of cores, they're using the same parallelization library. And so, this is like, there's a lot of, so what this basically says is that as a number of open offers, which is the batch size, goes into millions, the transactions per second are sort of managed to stay very high. And as you have more and more CPUs, you can do parallelization more and more efficiently. So we are a little bit far from where we started at the beginning, which is, we started like a very high level of DeFi. And maybe this is like a deep dive into if you believe my contention that these DeFi primitives are useful, then you are very naturally led to these new kinds of markets, which lead to new kinds of both optimization problems and computational problems. Yeah.
All these mechanisms are baked into the blockchain itself, in the smart contracts?
Yes, so I think, so this, so we made a system which actually does, so yes, it's all baked into the smart contract. So you can imagine like this entire market will be a smart contract. And the smart contract would have this code which executes. Now, in a permissionless blockchain, you have additional degrees of freedom. In a permissionless blockchain, sometimes you can have like not have a formal smart contract because they're doing consensus anyway. So a smart contract is sort of meant to ensure that things get correctly executed. When you're running consensus and you're relying on consensus anyway for like everything, then you can just say, okay, don't formally do a smart contract. Just have this piece of code. We all agree this is the piece of code we are running, and we're going to do consensus on the exact batch we are clearing, then the exact prices that we came up with, then the exact thing. And if one person wants to somehow unilaterally change the code and do something else, they cannot because of consensus. Now, so you have this lever. You can either rely more on consensus or you can rely more on cryptographic guarantees. But you can also convert all of this into a smart contract, which is like an exact cryptographic guarantee. So you're going to only run this code. Okay. I think I have more results about the design of CFMs, but I think I should move to my, yeah. So we have like a lot of work on how to optimally design CFMs and how to optimally combine them. And those results are all very interesting, but really they don't offer like any new perspectives. Hopefully it's already clear that these markets are interesting. Hopefully it's already clear that if you want to have a market like this, you have to carefully design it. You have to carefully design how to, like if you have some belief on how prices are going to evolve, you have to carefully figure out how this trading function should be designed. Okay? And so we find, we have algorithms for finding the optimum CFMM, the optimum trading function in expectation for a given set of beliefs on future prices. And so there was this question that got asked, why this trading function? And normally whenever you have a trading function in say any kind of formula in traditional finance, it depends on your belief about the future. So you have some kind of a prior belief on how the future prices are going to evolve. Then you can sort of figure out the trading function which gives you the best trade-off between risk and the fees you're going to collect if you are a market maker. And this was actually mentioned as like the ultimate result, and this is, we have a theorem which given your future beliefs can find the exact right trading function for you. Yeah? So I'm going to skip all that. I'm going to skip the rest of the optimization work, and I'm going to go back to the architectural part. Yeah? Yeah? And this would be like a good time to stop and take a couple of questions if anyone has any questions about say badge exchange. Yeah.
So the question is, assume that like there is, what I want to understand is this curve is accessible by different agents, right? So for example,
any agent can go and create a market, and any agent can then go and trade on that market. So, but these are two different roles. The person who created the market is the market maker. That person gets to specify the exact trading function and gets to specify the initial results.
So for example, if there is an existing market of rupees with micro bitcoins and somebody else also sets up a market, the person is pushed to use the pre-existing function if that market already exists, right? Otherwise, there could be advantages to some
There
points
could
in
be
the curve.
arbitrage opportunities. So what could happen is once I create this, please correct me if I am not answering your question. Once you create this market and you fix this trading function.
Yeah, let's say for a new asset or new.
But then you can also, but someone else can create another market with a different trading function. And there could be arbitrage opportunities between the two. You could have, these things might also be trading on a conventional exchange. And the price on this exchange may drift away from the price on the conventional exchange, which could create trading opportunities. And you're assuming that traders who are using the system will generally find the most favorable price and go there. And in the process, if this one is mispriced compared to an external market, then that would create an arbitrage opportunity.
So like the idea is not to decrease arbitrage opportunity, but like that is fine.
You cannot, whenever you have an automated market maker like this, arbitrage opportunity is what you're relying on for price discovery. So what you're relying on assuming as each time an arbitrage opportunity gets created, some trader comes and finds and removes it. Like this is the correct price should be here, the tangent is here. Some trader will come and move it there because that'll be profitable for them. They'll get a more favorable rate here. They can buy here and sell on the other market.
No, but for price discovery, I can also use this same function, right?
So you can use the mechanism by which this function will lead to price discovery is under the assumption, the efficient market assumption, that people, if this market is mispriced related to the external market, then people can come and trade on this market to the point where the price on this market becomes exactly calibrated to the external market.
Okay, got it.
I mean, you're saying it like it's a flaw, and it is a flaw. I mean, it is a flaw in the sense that there's arbitrage opportunity, that someone lost money. So it's, in that sense, it's a flaw, but it's by design. Yes?
So how does it extend for multiple stocks, like for multiple
So you can have many of these markets in existence at the same time.
Do you do like pairwise stuff, or
You can do pairwise comparison. You can do pairwise things by trading pairwise. You can also make more complex markets. You can also say XYZ equal to 10 to the power 7. And both these kinds of markets exist. You can also combine them with batch exchanges, which was going to be like, which is another part. You can say that you have batch exchanges which are composed of these kind of Uniswap markets, and you have batch exchanges, and you also have limit orders. And you can somehow have limit orders, and if these limit orders don't have perfect liquidity, which is how I interpret Vineet's question, like there's a lot of price volatility from batch to batch. But if you have a small number of these automated market makers thrown into the batch exchange, then they guarantee some price stability from batch to batch. And you can actually compute, clearing prices in the presence of both normal limit orders and these kind of markets. Yes, sorry, go ahead. So generally, generally no, because generally if you're allowing arbitrary external macroeconomic phenomena, then it's not an automated market maker. It becomes like a bank where you go and the bank quotes you and exchange it at that day, and you can take it or leave it. Yeah? So generally, you could do it. You could create a smart contract of that type, but I would not call it a constant function market maker. So then. Getting back to the architectural issue, right? So given, I think a lot of these DeFi primitives are really useful. Okay? Let's revisit some of these applications, right? Like collateralized assets, that could be a very powerful investment tool. Multi-currency exchanges, escrow, programmable payments, the new kinds of loans. But if India's regulatory stance is a guardian onto cryptocurrencies, but they want to do programmable payments, how would you do it? Yes, go ahead. They just specified. So this K, if you assume, if you are in, so this is called a constant product market, right? In this one, you don't even have to specify the K. If xy equal to K, let's say your xy is 10 to the power 7, as a market maker, you just come in and you throw in some amount. You say, okay, I'm throwing in 10 to the power 3 microbits of Bitcoin and 10 to the power 4 rupees, and I want to make a constant product market. That automatically dictates that the K has to be 10 to the power 7.
And how are they finding these amounts of the, like they're just listing?
So how do they decide to put 10 to the power 3, 10 to the power 4? I mean, hopefully they're using some market insights to figure out what the right thing is. But here, for the purpose of this example, with 10 to the power 3, 10 to the power 4, the implied market price is the tangent of this curve. The implied market price here happens to be 1 micro Bitcoin equal to 10 rupees, which is roughly the price of Bitcoin right now, I think. And so, I could be wrong, I could be off a little bit. And so, I just designed this initial thing to make sure, normally you would make sure that the initial tangent, at least you don't have an arbitrage opportunity in the beginning. So you want to make sure that when you create the market, the implied price by the tangent matches the market price. So that would be like a simple thing to do, but there's nothing which requires them to do it, but that seems like a sensible thing to do. If they do anything else, then immediately somebody will come in and move it to that price and you'll immediately lose money. Yes?
For example, if I set up a market and have a different function, which is like, so there needs to be a starting price. The starting price is existing based on the existing valuation, right?
Yeah.
So for example, if I give a function, and the function is obviously visible to the other, let's say bots who are executing.
Yeah.
So the function has, so imagine the function like the curve of the normal distribution. And so is it like, for example, if you can see a part of the function is very sort of lucrative to trade on. So does it, like, I'm just trying to understand, is it, does it happen that, okay, to reach that part, there are suboptimal trades executed by the bots?
I mean, I know, I mean, these things are big enough. Like I said, the volume is $400 million, so they're like automated strategies. Like, so I don't know what people actually do in practice. Probably no one does. But maybe to answer like a related question, this curve is now important enough that instead of using xi equal to the power 7, people now design this curve on the new version of Uniswap v3. Instead of having just one function, they allow you to design these piecewise functions, where the functions are different in different areas. And so the market makers are definitely doing it. Whether traders are doing it or not, I don't personally know, but given that there are automated strategies now and people are making models to trade on these things, I'm assuming yes. So going back to like the more fun architectural question, right? Are permissionless blockchains still the right architecture to deliver DeFi in an Indian context? Okay? And like just the way I pose this question, you can imagine that the answer is no. And so we have this proposal. Okay? I mean, I don't know who this proposal is to, but we have a proposal anyway. And the proposal is to have this kind of architecture, especially in India, because there's some unique reasons why this kind of an architecture fits in India, which I'll describe in a minute. It's a centralized smart contract platform for India. Okay? It gives you all the power of crypto and none of the chaos. The central idea is to re-examine this link between blockchains as a substrate and DeFi as the application. And the claim is that this link is just happenstance. It's not, there's no reason why DeFi can only happen on blockchains. Okay? So instead of operating a blockchain, either permissionless or permissioned, just operate a centralized smart contract server as the base technology. Okay? And this is what's generally called in this space, is called layer 1. So layer 1 is a centralized smart contract server run by a trusted technology-savvy organization like, for example, NPCI. And that's all they're doing. They're not like doing any stable coins. They're not doing like any other kinds of fancy products. They're selling the smart contract server. And basic smart contracts like stable coins with verified reserves. And someone like NPCI can do it. They can verify reserves by placing holds on a bank account because they already have the UPI infrastructure. Payment on delivery, secured loans, these basic smart contracts are already pre-approved and anyone can run them. Others can be approved on a case-by-case basis. One of the biggest problems with DeFi tend to be off-ramps and on-ramps. How do you get like from a fiat currency to a DeFi currency? How do you get off? Okay? You avoid all of them because you can do UPI payments because it's NPCI. It provides this base technology for safe, regulated DeFi and nothing else. Okay? And that fits with the UPI philosophy. Okay? I think one of the reasons UPI really took off is just a payment protocol. It's not a product. Okay? UPI didn't really try to make a phone pay. They didn't try to do like EMI on top. Okay? And that really fits with this idea that you have a centralized smart contract server and do nothing else. Okay? And everything else let somebody else do it. Okay? individual banks and fintech firms can build more complex products that they want by either introducing their own smart contract servers or on top of these basic smart contracts as layer 2 technology, which is actually already very common in blockchains. Implementation is fairly easy because any blockchain-based smart contract platform can become the centralized server by just turning off the consensus layer, yeah? And adding more support, yeah?
How do you make sure that smart contracts are not tampered with? There's no consent.
Who is you?
I mean, the users.
Well, the users use UPI, so the users trust NPCI to be like a basic good player. But also, smart contracts also provide cryptographic guarantees. So,
Do you not need a consensus for that?
no, so some guarantees you can do without consensus. So, for example, if it's you can have a cryptographic guarantee saying nobody else has the key to update the smart contract server. So now if NPCI, I mean, all the money belongs to RBI. If they decide to steal your money, they'll take it anyway. But as long as they're updating as long as they have to show that they're updating the smart contract server correctly, okay? And you can publish, even in the centralized smart contract server, you can publish proofs of correct execution. And the nice thing about using an existing blockchain infrastructure, they already have support for publishing these proofs. So you can publish proofs of execution, anyone can verify them. You have to have the right keys to update them. To issue a key, they can do KYC, know your customer, the way they would do it. You'll have to add some more support for cryptographically verified execution. But these cryptographic tools exist which can stand in for consensus. We have started developing a prototype using this open source Hyperledger Fabric blockchain infrastructure. It's very simple. My students say that it's just a matter of deploying it because everything is already there, right? They just turn off the consensus layer, and they might not even turn off the consensus layer. They might just set k equal to 1 in the consensus thing, and it just does consensus itself, which might be like a little bit inefficient, but it's fine. For any layer 2 application, this presents a standard layer 1 interface because people are already building on top of Hyperledger Fabric as a blockchain, as a layer 1, yeah? Allowing easy development and deployment of L2 services by individual banks. Layer 2 applications can provide additional product functionality, including an anonymized layer for specific applications like healthcare, right? If you want anonymity, you can do it as a layer 2 service as opposed to a layer 1 service. And it's like gives a clean system architecture. The Reserve Bank of India governs everything, has regulatory authority and oversight. Someone like NPCI runs a smart contract server and does nothing else, just runs a smart contract server. Just like UPI, just runs UPI and does not do like EMI and whatever. And then the layer 2 banks then develop their products. And some smart contracts like stablecoin are already integrated. There's already an audit trail. There's some KYC AML layer that NPCI runs. And you get full regulatory compliance and instant settlement because of the UPI off-ramp, on-ramps. Okay? And so any feedback, implementation help, advocacy help, if anyone has the phone number of the governor of the RBI, wants to call them on our behalf, it'll be very welcome, and any questions are also welcome.
A general question that's not really technical, but for example, if you say to get your transfer or whatever happens, you can still go to the bank, confirm your identity, and probably take that
Yeah.
out. But as far as I understand, your key is your entire identity. If you lose your key, you lost your wallet, you now you are.
Yeah, it's a problem. That's a problem. It's going to be a bigger problem than on blockchains. If NPCI is running it, I mean, you would assume that if NPCI is building something like this, you would assume they can figure out some way of securely reissuing your key based on your Aadhaar card or something.
So you trust them with having an IC?
Yeah, I mean, you already trust them. So this is where some of these arguments against having a centralized server are more salient in settings where you're not already doing it. But here, this is already running UPI, which you're already using day to day, every day for buying like tea and samosa. So it's it's not clear. And there are going to be applications where you don't want the government to know. And for those applications, you can still go and use Bitcoin. And there are going to be other applications where you want some limited privacy because privacy is important, and that you can do on L2.
And then you do that off this chain.
So no, you can have an L2. You can have an L2 server which anonymizes. So you can L2, for example, you want to do stablecoin transactions in an anonymous way. If the regulators allow it, you can have an L2 server that rolls up all the transactions that it receives and does transactions with the L1 server. The L1 server, which is run by NPCI, doesn't know the identity of the people who are doing L2 transactions.
There's no way the L1 server can interfere.
No, I mean, they can interfere. They can, monitor all the IP addresses on all the routers in a country. I mean, the government has a lot of levers to monitor you if they want, but that they can do on Bitcoin for Bitcoin transactions also. So you can take any Bitcoin technology like Lightning or whatever, and you can run it as an L2 on top of this L1. But then the government has to allow it, so it'll probably be for like very specific use cases. But this is like a little bit beyond my pay grade. This would be like the kind of thing that's what I'm convinced that this is the right architecture. A lot of these sensitive details would be someone else's decision.
I mean, even with the consensus layer on, there is the off-chain to on-chain transaction that has to be trusted by some central authority, right?
You mean currently?
Or smart contract.
Currently.
Yes.
Yeah, so currently these off-chain and on-chain, off-ramps and on-ramps are a big problem for these cryptocurrencies. And people say this is a big, but it wouldn't be a problem in this architecture because UPI is already there.
Is there any reason why the curve needs to have a single path for both upward and downward transactions?
Yes, so you can prove that this curve has to have this general shape.
So it can't be like sort of a hysteresis kind of curve where you're going down.
No, it has to be like this concave shape.
Okay.
This broad concave shape has to be, you can formally show it. That comes from some, if you don't, then you can have some local internal arbitrage. So the kind of arbitrage you were concerned about earlier was what if there's an external market? But you don't want to have like internal stuff happening. Okay. And so this form is fixed. But within this form, you can have a curve which looks like this, you can have a curve which looks like that, you can have a linear curve.
Okay.
But this general curve shape has to be there.
No more questions. Let's thank the speaker.
Oh, yes.
So, just a second. So we now have a break till 11, and then we'll start off with Professor Sarah and her session. So please be back by 11. You have 20 minutes. Thank you.
Did I pronounce her last name correct?
Yes, yes, yes.
She just joined, I was told, just 2 weeks ago as an assistant professor in the ECE department at Carnegie Mellon University, and has a joint appointment with engineering and public policy department as well. She got her PhD from EECS at MIT and spent some time at Oxford before starting the position at CMU. Her research focuses on machine learning and, more importantly, accountability in AI and policy regulation, and that's what she will talk about. Thank you.
Thank you so much. I want to start off by saying thank you so much for having me. This has been really, really wonderful, and I'm very happy to speak here today, and it was really nice to meet everyone so far. Okay, so this might be a slightly out of distribution talk. I'm gonna, half of the work that I do is in ML and CS, and then half of the work that I do is in policy and law. And so what I really want to talk about today, because a lot of people who work either in ML or in policy have questions usually about how do we actually bridge the two, how do we do research that meaningfully contributes to policy and law. That's kind of what I wanted to showcase today, maybe 3 different flavors of research that you might be interested in if you wanted to work in this space. Okay, so AI has moved from the lab into our homes and institutions, and there are a lot of impacts, right? It intervenes on our private sphere, it has profound economic impact, it affects our rights and livelihoods, harms consumers, poses societal risks, raises existential questions. This is nothing new to many of this audience. And of course, these are kind of like the harms and the negative consequences that might arise from AI. But there are obviously a bunch of really great things that come from AI. And so really the question is, how do we help curb these harms to best allow for innovation? And this is kind of the cycle that a lot of people think about, right? You have AI's growth, adoption, and impact. These inevitably have some sorts of unintended harms and externalities, and we turn to regulation and litigation, both in the public and at the private level, to actually allow for growth, adoption, and impact to continue. Okay, so there's a lot of growing attention to what people now call AI policy, and I just wanted to list a bunch of common areas in AI policy, because a lot of times when people think of AI policy, they actually think of only 1 or 2 of these things. So there's risk management. So think about the risks of AI, and you can turn to the EU AI Act and see how they are asking for risk assessments, or Biden's old framework, which has since been removed, but that looked a lot at sort of risks. You can think about AI innovation. You can think about national security and international policy. You can think about monopolies and antitrust, manipulative and unfair practices. So a lot of times the focus here is on Amazon, Meta, Google. There are various mental health and self-harm questions arising around social media. CSAM, or child sexual abuse material. Right now there's copyright and intellectual property is a very hot topic. There's also name, image, and likeness, which is the use of someone's image, or let's say Scarlett Johansson's voice, to power ChatGPT's or GPT's voice. So those are sort of legal questions as well. And there's also this increasing phenomenon of robo-scams. So you can have these sort of robot voices that are scamming often the elderly out of a lot of money. Okay, so, and many more. And really what I want to say today, I can't cover all of these, but thinking about a lot of them. So if you're interested, please get in touch. Okay, so today I want to maybe have a conversation about 3 routes to AI policy research. I'm going to focus probably mostly on the first one, but we'll take a little glance at 2 others. The first is how engineering can help reduce gaps in AI governance. So let's say you feel like you're an AI engineer, but you want to address this area. What can we do from an engineering perspective? The second is thinking more about kind of the shape or economics of the growing AI industry, so kind of taking a bird's eye view. And the last is doing sort of more hands-on empirical studies, so studying the effect of AI, let's say, on media and democratic institutions. Okay, all right, so let's start with the first, how engineering can reduce gaps in AI governance. This is a paper, this is largely based on this paper with wonderful colleagues back at Stanford, Salil, Zaina, Ananya, Percy, and Dan. Okay, all right, so the goal of this is to think about evidence in litigation. And what's the importance of evidence? Well, most of our legal systems operate under some notion of burden of proof. So the raising and producing of evidence and convincing the fact finder, like the judge or the jury, that that evidence is supporting your claim. In AI-related cases, and we did sort of this legal case analysis on this in the US, gathering enough evidence to meet the necessary evidentiary standards is often really challenging. And so this is exacerbated by the fact that developers very, very, very closely guard access to data and models. And they basically constantly claim that they're trade secrets or that they're privacy concerns, so you can really not access their models or data. Okay, so to illustrate this clearly, let's look at something called Title VII in the US. And bear with me, maybe the next few slides, next 5 minutes, we'll delve a little bit into the US law, but then I'll show you how we can actually formalize this problem and then develop a technical result from it. Okay, so who here, this is a different audience than I'm normally speaking to, who here knows what Title VII is? But even in a, okay, I don't see any hands actually. Okay, great. That makes this slide very relevant. All right, so Title VII in the US Civil Rights Act prohibits employment discrimination based on race, color, religion, sex, and national origin. Sorry? Nope, age is not included here. Age is included in some other discrimination law, but not for employment discrimination. And one thing I would like to point out is that if any of you have heard of or studied algorithmic fairness, Title VII, I would argue, is this sort of underlying law that basically inspired that entire field of research. So if you wanted to know any law, it would be this one, this employment discrimination one. Okay, and so employment discrimination covers hiring, promotions, firing, et cetera. Okay, so in the US, there's very complex procedure for proving that employment discrimination occurred, but I'm gonna simplify it. So there's, the hundreds of writings on in Title VII, I'm gonna simplify it. And there's something known as disparate impact doctrine, and this is what is usually applied to automated or algorithmic systems like AI when you're considering employment discrimination. Okay, so what are the 3 steps of disparate impact procedure? So you go to court, the plaintiff is the person that is saying, I was discriminated against. They must first prove something known as disparate impact. This is often what people study in algorithmic fairness, or like in the early days of algorithmic fairness. They basically want to show some sort of statistically significant difference between the outcomes of 2 populations, where that's on the basis of one of these things, sensitive attributes up here. Okay, so this is not what I'm going to talk about today, but this is the first step, has been a focus of 10 plus years of research. Okay, so let's say the plaintiff successfully shows disparate impact. The burden of proof now shifts, or the burden of persuasion. The burden of proof. The burden of persuasion is one part of the burden of proof, but anyways, the burden of proof shifts to the defendant. And the defendant now, this is the employer, needs to show business necessity. So they can actually say, this discrimination, this statistical difference that you have detected is justifiable because it's actually for a business reason. So for example, let's say you have like a moving company and you find that you have more men than women who are in your moving company. You might say, well, actually, that's because of the physical differences that you often observe between men and women. And so this is actually the basis for one of the well-known cases for disparate impact, where there's a woman applying for a police force, and she was able to show that statistically more men than women are hired. But the police force responded by saying, the safety of our citizens and other officers is really important, and so strength and agility is really important, and that tends to kind of occur more frequently with men than with women. Okay, so this is the business necessity defense. All right, so then if the employer is able to show this, the burden of proof shifts one last time back to the plaintiff, and this is the final step, and this is what the plaintiff needs to show in order to win this case. And I want to emphasize that actually a lot of people don't understand the law around discrimination, and they often think, okay, well, you can show discrimination wherever, whenever, it's super easy because you just have to do this first step. But it actually is pretty hard because you have to show this last step. And this last step is that the plaintiff must then prove that there is a less discriminatory alternative that the defendant could have adopted. And the burden of proof here is on the plaintiff. Okay. Any questions so far? Yeah.
The third part, I think it's very difficult.
This is our focus. Yeah, exactly. It's very difficult. Okay. All right, so less discriminatory alternative. This is our focus today. We're going to call it an LDA. This is defined as the language isn't exactly this in the law, but effectively we can interpret it as an equally high-performing but less discriminatory option that can be found with reasonable effort. So you don't need to pay $1 bajillion to find this less discriminatory alternative. Okay, and like observed, this is pretty hard in AI-related cases, right? A straightforward interpretation of this is that the plaintiff must produce an AI model that performs just as well, but is less discriminatory. And I would argue that that's kind of the focus of a lot of people's entire PhDs. So to expect a plaintiff who doesn't really have expertise or resources in this area is pretty difficult. Okay.
So this high-performing aspect requires private knowledge of the business?
Good question. I don't think it necessarily requires private knowledge in the sense that the way that I would view these 3 steps is by the time you get to the 3rd step, the plaintiff has established some notion of discrimination. So they've picked some notion of fairness, basically, and they've given you a number. And then in the 2nd step, the defendant responds by saying, here's our notion of performance, and they give you a number as well. So by the time you get here, those 2 have kind of been settled, and you're trying to say, there is a less discriminatory alternative that would be below both, or above the performance number and below the discrimination number. Okay, and so just to really drive the point home, why is this difficult? This is difficult because trade secrecy often blocks access to models and training data. Privacy additionally blocks access to training data, and you often have limited resources as a plaintiff, and so you don't have as much access to compute. This makes it hard to train comparative models from scratch or tinker with the current model yourself. Okay, great. So our goal is to show the developer could have found a less discriminatory alternative with reasonable effort despite a low number of resources, data, and model access. Okay, so let's make this sort of a little bit more formal. The employer's argument is that to reduce disparate impact, the AI system must sacrifice performance. This is kind of a claim about closeness to a Pareto frontier. So let's imagine that you have 2 axes. You have loss on the y-axis, and you have a fairness gap on the x-axis. So you want, in an ideal world, you want low loss and a low fairness gap. So bottom left is a good thing. Okay, so let's say that steps 1 and 2 establish that the existing AI system falls here. So this is the fairness gap that was established, and this was the performance that was established. Then you might ask, okay, well, where does the Pareto frontier fall? Is the Pareto frontier this hypothetical line, this orange line, or is the Pareto frontier this hypothetical line, the red line? And if it's this hypothetical line, the orange line, or a curve, then it implies that actually you cannot lower fairness without sacrificing performance. And of course, if it's the red curve, then that tells you that there's this gap that you can actually improve upon. Okay, so does this make sense? Great. So going back to why this is hard, the first challenge is the information asymmetry, the fact that developers fiercely guard access to model data and documentation. So what we're going to propose that actually instead of finding an alternative model, so training an alternative AI system, which is hard, we're going to show some notion of existence. And kind of conceptually, maybe this is a little bit easier. And the way we're going to go about it is try to find where the Pareto frontier falls. Okay, so why is this hard? This is hard because usually finding the Pareto frontier is actually a very difficult operation that is very expensive. So what is often done empirically is you actually train a bunch of models yourself. Each of these models I'm going to represent by an X. And then you trace this sort of lower left curve, and you say that's where the Pareto frontier falls. But you can imagine this is just as hard as finding the LDA, right? Because if I'm able to find something that's sort of lower to the left, then why do I need to have found the entire curve to start with? Does that make sense? This is sort of a computational issue as well. Okay, all right, so that's what we're going to get to with challenge 2, which is this resource asymmetry. Plaintiffs often lack resources, and methods for actually finding the Pareto frontier are no easier than finding an LDA itself. So what are we going to do here? What we're going to do is we're going to basically propose a solution around scaling laws. Now, who has heard of a scaling law? Don't be shy. Okay, all right, good. So maybe I should take a little bit of time to explain what a scaling law is. Scaling law is this fancy new AI term that is not really that new of a concept, but it sort of says if I add more parameters or if I add more data during training, how does my performance improve? So how does my loss decrease? And the original scaling law paper was effectively motivated by I think it was coming out of DeepMind, I want to say. It was either DeepMind or OpenAI. And they basically said, we can't afford to do this like very, very high dimensional search over all possible parameters, data, models, model sizes, and so on. So we need to develop a predictive model for the right number of parameters, so the size of our model to train, and the amount of data that we need to gather if we want performance to be sufficiently good. And so they developed this predictive model that they called a scaling law. Okay, so how does that apply in this context? Well, let's assume that you don't have much access to the model, but you are able to convince model developers to give you two things. They're able to tell you, sorry, I'm jumping ahead of myself. Okay, why don't I show the figure first? All right, so what does the scaling law say? The scaling law says, I fit a Pareto frontier based off of small models and small data sets. And then I am able to extrapolate where the Pareto frontier falls for large models and large data sets without ever having to train a large model on a large data set. So this is sort of the low resource regime, and I'm using it to extrapolate. And the hard part is figuring out how to extrapolate, so I'll get to that in a second. And the procedure would then look like this. I am only given information, N and D. Capital N is the size of the model that the employer has access to. D is the size of the data set that the employer has access to. And then I'm able to kind of extrapolate based off of just training small models of size little n and of size little d. Okay. All right, so this is scaling law, and this is not empirical. So what we're going to do is we're going to demonstrate that it's possible to derive effectively a closed form scaling law. And so this notation actually doesn't really matter unless you want to sort of look underneath the hood, because I'll explain the equation super, super simply. But again, you have some training data set size, target, capital D. You have some model class that you know the model is coming from. You have your notion of loss, the y-axis, and you have your notion of a fairness gap, which we're going to treat as demographic parity. And for now, we're going to use binary cross-entropy loss, which is appropriate for this setting where you're hiring or not hiring, promoting or not promoting, firing or not firing. Okay. All right, so this is our result stated with the assumption stated informally. So under the assumption that the model class is sort of symmetric with respect to the data generating process, which you might assume to be true for universal function approximators, you get this result. Okay, so let's just dissect it really quickly. What do you have on the left? You have loss. What do you have on the right? You have this complicated expression in terms of delta. That's your y-axis on the plots that we've been looking at, and the delta is your x-axis on the plots that we've been looking at. So basically you have loss stated in terms, y is stated in terms of x, in terms of a bunch of other things, including these constants c prime, and this capital B. Okay, so that's actually really nice, that's really easy. What I mean by constants is that these things are obviously, these are dependent on your distribution of interest P, but they're not dependent on delta. And so this is effectively a scaling law. Why? Because you have 4 constants, but 3 of them don't depend on your model class, F, or the size of your data set, D. And these are the things that scale, right? Everything else doesn't scale.
So what does symmetric mean?
Symmetric, basically, there's like a certain term with respect to loss. So we basically just like decompose this, which is binary cross entropy, into a bunch of terms around like entropy and so on. And one of those terms is basically a difference between something with respect to your test distribution P and something with respect to this like tilted distribution Q. And all that we're saying is that this one kind of maps to 0, and the only difference between them is P and Q. And that's what I mean by this. There's this symmetry with respect to this term that empirically we're going to observe it's pretty okay to make this assumption. And all that it's sort of saying is that when you train a large language model, as long as you're using, like, let's say, the right regularization, then the underlying distribution shouldn't affect your ability to train the model well too much. So you're like symmetric-ish with respect to the data generating process. Good question, thanks. Okay, so again, you've got 4 constants. 3 of them don't require the scaling. So you can fit 3 constants to small data sets, small models. And then from known scaling laws, you replace this last constant with 1 over square root of n plus 1 alpha over square root of n plus beta over square root of d. In the end, this actually just turned out to be a very nice scaling law in the sense that it was linearly separable in that way. Okay, so just to revisit our very simple procedure, this is a pretty, yeah. Oh, it's just nice because the scaling part separates out. It's just additive. That's what I meant. Okay, so just to return to our simple procedure, what we effectively saw was, okay, we had this dream of let's take small models and data and do something in this low resource regime, and that will tell us where the Pareto frontier is for large models and large data sets, and that can help us infer where the Pareto frontier is and therefore understand if a less discriminatory alternative exists without actually having to train any big models from scratch. And what allowed us to do this was this sort of nice closed form upper bound that tells us approximately how L scales with model size and data. Okay. And last thing we did, I mean, this was mostly a result around that theory result, but the last thing that we did was we tested this empirically. It's not a super extensive test. There's not like gigantic models here, but we did simulations on models we could train on with our limited compute, and are able to show that the scaling proceeds as we would expect it to. These were simple MLPs. Yeah, I think more extensive experiments are needed. Yeah.
Shows the existence of an LA, right? But we haven't addressed the reasonable effort part.
Excellent. Yeah. So because I wanted to show kind of like 3 different types of work today, I'm zooming through this like a little bit quickly. But I think there's some notion of distance from the Pareto frontier that could help quantify reasonableness. There's another thing that you can do, which is what we haven't done here, but you can actually kind of use like a bootstrap procedure to basically get a notion of like confidence bands around each of these, and that will tell you a little bit like what closeness even means and like how reasonable it is for someone to have found an LDA with the same amount of compute, same size model, same size data set as they originally had. Yes?
I have a question regarding the inequality in your theorem.
Sure.
What we want, if I understood correctly, is to characterize the Pareto boundary, right?
Sure.
But this is just, how do you know that this inequality is characterizing the Pareto boundary? It's not just, part of the Pareto domain.
In the sense that you're saying, why is it's an inequality?
For your work is to actually prove that the Pareto boundary has some shape, but then you need to characterize it.
Yeah, yeah. Yeah, so I mean, we're trying to argue, and most of the details are in the proof, but that this is like a pretty good upper bound. And there's almost, I don't want to say it's like tight, but there's like a condition under which it actually is equality. But I don't want to say it's tight because I don't think that condition tends to exist, but it's like sort of tight. And so that's why we think that this is like pretty good, and at least sort of like somewhat empirically it tends to be pretty good. And I don't want to overclaim this slide at all because I think we should do more extensive studies. Yeah, thank you. Okay, all right, so that's thread 1. I don't even remember if I have a summary slide, but let's see. oops, going backwards. Okay, great. And so what I really wanted you to take away from this, and I'm happy to talk about more details offline, is that evidence is at the heart of law and policy, and this is what gave us this motivation to study evidentiary burdens on plaintiffs who are like a lot less well-resourced than the AI developers and deployers that they're going after. And that if you're an engineer and you're saying, okay, I can't do policy, I'm not trained in policy or law, what can I do? You can maybe say, okay, how do we even the playing field a little bit more and give plaintiffs tools to get evidence so that they can win their cases. And this is, I don't think a universal solution. I think this is actually a very, very small piece that said, under this set of conditions, here's what you might want to do. But I think even in this Title VII scenario, there's like a lot more that could be done. All right, so let's move on to part 2, unless there are any questions. Yes?
Why would the defendant have, if you're so far within if you're off the particular even in the margin, why wouldn't they have at least improved the loss?
Oh, why wouldn't they at least move downwards?
If it's reasonable effort, they could find better.
Sure.
Then wouldn't they have put a reasonable effort already in the loss?
Yeah, that's a good question. I think it tends to probably mostly arise if you're like close to the right-hand side where you've gotten pretty low loss, but there's like a lot of room to move laterally. Yes?
So when you say providing winning solutions to the plaintiffs, is the goal for experts being plaintiffs or the common person also can use these tools? Is that the goal?
The goal is for common people to be able to, if we help build a suite of tools, then they can use it. I just wrote a sort of law piece around what are like the common barriers that people face when they go and try to sue like an AI developer or something like that. And expertise is sometimes blocked, but is probably the least hard to access. So I think if you're able to access someone with expertise to help you on this, that is much easier than getting like model access or data access. Yeah. Good question. Yeah.
What are some of the metrics of measuring fairness in real-world scenarios?
Yeah, there are a lot of ways of measuring fairness. We use demographic parity, and that's actually very well motivated in this setting. Demographic parity is like the simplest thing you can think of, which is sort of like the difference in selection rates between one group versus another. And this is the simplest thing, and so computer scientists often don't like it, but it is the thing that the courts have used historically. And the second reason I think it's a reasonable thing to think about is the next more sophisticated thing is like true positive rates, false positive rates. So trying to see if actually the selection rate might be different, but is at least the true positive rate, false positive rate matched across populations. The hard part about that is you need access to ground truth. And so you need to have access to, let's say, this person would have been a successful employee if I had hired them. But that is like often very difficult to get, or you need some complex procedures to infer it. And so courts are like less amenable to looking at that metric. And of course, there are many more sophisticated fairness metrics that people have studied all the way over to like multi-calibration and so on. Does that answer your question? Okay. Okay, great. All right, so track number 2, or thread number 2, is tracking the sort of shape of the growing AI industry. And this is mostly based off of 2 works, one of which was done at MIT with Aspen, Andrew, Isabella, Luis, and Alexander. And the second work is, I'll talk about a little bit, but is going to come out of Stanford during my postdoc. Okay, so what are AI supply chains? People, by the way, refer to things like AI supply chains under a variety of names. So I just want to kind of sort of set that disclaimer. AI supply chains in our work is what we refer to as the complex network of AI products and services that integrate and produce AI. So like the super canonical example is Organization 1 produces a pre-trained base model M. Organization 2 curates some specialized data. Organization 3 fine-tunes M on some specialized data D. So you have three organizations, they're creating this sort of virtual, non-physical supply chain. And from a historical perspective, this is like not something that is that new. I mean, obviously supply chains are not new, but the tradition of outsourcing ML work even has developed over decades, right? It began with data work. I would argue that the gathering of data sets was like a huge innovation that allowed widespread training without having every individual researcher have to gather their own data set, which is very expensive. Then extended to things like Mechanical Turk that allowed automated labeling, crowdsourced labeling, and so on and so forth. And eventually extended to even model training. So now we take these models and we post-train on them. So someone has done effectively a lot of the work for us. And so for the most part, this was gradual until 2022. And of course, with the release of ChatGPT and so on, there's this explosion of AI adoption, not just in labs, but in the real world. And this has led to the emergence of complex AI supply chains, which was sort of this thing that was noticed by this economist who was on this paper working with us. And that's sort of what spawned this area of interest. Okay, and supply chains are not a bad thing. They actually signal the healthy growth of the AI industry, right? They improve efficiency by distributing tasks across people, and they allow for specialization. And what we do in this paper is make some very, very simple observations and provide some pretty trivial results. So first thing we say is like these are directed graphs, and so we can build off of this language and literature around network analysis. Before I go further, I want to mention a few implications and previous works that look at supply chains. So Lee, Cooper, and Grimmelman in 2023 have studied copyright in the context of supply chains. So if you have a lot of individuals contributing to a system, how is credit attributed? How should royalties be distributed? Who has ownership over AI creations, and more. Witter and Nafis discussed how AI supply chains disperse accountability in these sort of non-modular ways. They wrote this beautiful piece on that back in 2023. There are some potential implications on regulatory requirements, and that's what I'll talk a little bit about today. So placing regulatory requirements on upstream models may not actually have the intended effect. And so just to double click on this for a second, so how do upstream constraints actually affect downstream actors? So you can think of this upstream model at the top of the supply chain and some fine tuning and development occurring as you move down the supply chain. And you can imagine that those upstream developing the base models, these are like, OpenAI, Amazon, Anthropic, Thinking Machines, and so on, they have their own design criteria. And so they have these, regularizations or constitutions that they're trying to satisfy. But their design criteria may not actually match what downstream developers or model deployers want. So, for what it's worth, I do believe that upstream model providers, it's impossible for them to account for all possible downstream desiderata. So it's hard to hold them accountable for that. And so we kind of study this in a very toy setting. Let's imagine you have some input X, you have some base model FP, and you have some fine-tuned model V. V is for the sort of the vertex of interest, and P will refer to parent, so that's how you can remember that. And for simplicity, let's say that FP and FV both take in X's and output scalars. So they both take in some applicant's information, and they output some scores of some sort. So let me just make this concrete. Like, let's say that you have this model, downstream model, that is trying to decide whether to hire an applicant. And so you have all their applicant information. But in order to hire the applicant, you actually use some sort of like video interviewing system. And so this parent, this company that's developed this sort of video interviewing system that takes in a video from an applicant and then gives a score, is your parent model. Sorry. I take that back. I'm confusing two contexts. I will get to that one in 1 second. Actually, this setting, you have a parent model and a fine-tuned. So you have a parent model, a base model, and your fine-tuned model, both of whom take in X, which is like the resume and video application. Okay. All right. Okay. So we were talking about upstream constraints and downstream actors. So saying the base model developer, OpenAI, has some upstream constraints they're trying to satisfy, and your downstream actor has some other constraints. So what do we mean when we refer to constraints? We need to formalize this. So in this toy example, we formalized a constraint as a conditional independence. So f of x is conditionally independent of x1 given some other random variable z. And so conditional independence is nice, and we chose it because it encompasses various types of structured learning, for example, in causal inference. And additionally, it's nice because it includes notions of algorithmic fairness, right? So if you take z equals y, or z equals the empty set, and you let x1 be the sensitive attribute, you are going to recover equalized odds, which is a notion of fairness, or demographic parity. Okay, so this is the notion of constraints that will be used to theoretically formally analyze the setting. Second thing we need to actually abstract away is what is a base model? Here we're using a pretty common representation for a model, which is saying that fp of x is the sum of a bunch of basis functions multiplied by some scalars summed over I. So this is actually just one long vector. And this is shown to be a universal function approximator as n goes to infinity under certain regularity conditions and sufficiently rich basis functions. So this is sort of the toy model that we adopt for our analysis. And the second thing that we do is we adopt a toy model for fine-tuning. So this is also something that we've seen in the sort of literature on studying deep learning models. So again, this is your base model. It's just the combination of a bunch of basis functions operating on x and then some weights. Fine-tuning can be potentially theorized in some settings as you aren't changing the basis functions phi. These are coming from your base model. But what you're doing is you're effectively learning weights vi. And the most easy justification for this is when some people do fine-tune by just relearning the last layer of weights. But it's sort of adopted otherwise as well. Okay. All right, so very informally, there are two implications that come from an analysis of this sort. So again, using that abstraction of a base model and fine-tuning and constraints, meaning this sort of conditional independence. You have two conclusions. One is consistent with the literature, and that's the first one, which is that you can undo upstream constraints, right? That's kind of well known, right? If you train your upstream models to satisfy demographic parity, or you unlearn something with your upstream model, you can actually relearn it downstream. You can undo demographic parity fairness. You can relearn whatever you have unlearned. So this is good, actually. We're glad that this came out of a result because that's consistent with existing results. But the second thing, and it's actually kind of going back to Pareto frontiers, is that there may be a cost to doing so. So by undoing,
your basis functions were different for the upstream model and downstream model, then would this result supposed to?
are you talking about 1 or 2? I think if you allowed your basis functions to vary, 1 is even easier. If you allow your basis functions to be relearned, 1 is even easier because you're effectively allowing retraining of everything, both v's, the weights, and the basis functions phi. That's a good question. I think effectively if you allow relearning of phi, then you are constraining your model, and that actually makes 2 maybe harder to show, which is that it still has a footprint. So you undo it, but it leaves a footprint, and actually you will sacrifice on some other axis. And this is very informal, but you can kind of see it in literally the weights. There's sort of constraints on the size of your weights. And this is also kind of consistent with literature and maybe encourages us to look a little bit closer when we read those papers. There are some papers that say you can unlearn this or you can undo fairness. But what they don't look at is well, what is the implication on other attributes of the model? And we're arguing that it actually does constrain your model in specific ways. Okay, so that's case study number 1. Case study number 2, I'll skip through that. Case study number 2 is on information passing. So we do this via explainability, but our main message is that you might want to pass information, like specifications about your model, along the supply chain. Is information passing going to maintain the same level of granularity and accuracy as you pass it? And so we look at this through explainability. So you're going to pass explanations down the supply chain, and again, very trivial result that these explanations and their fidelity is going to degrade as you pass them along the supply chain. Okay, so maybe I won't spend too long on that because I'm running out of time, but this is the setting that I was accidentally explaining for the first setting. So it's similar. You have an applicant X, you have an organization V, and you have a decision FV on X. So you're deciding whether or not to hire this applicant or something like that. You have V, and V is using some outside organizational tools. So they're maybe using some video interviewing tools to interview their applicant or something else. And so V is using some parent models. And the parent models are passing back some score on the resume, on the video, so on. And then V plugs that into their simpler algorithm, and out comes their decision or some recommendation. Okay, so effectively you can imagine f of V as this sort of composition of functions where P1 through Pn are V's parents. The difficulty here is that you're also, let's say, required to pass explanations because the downstream actor is required to explain their decision to the applicant. So that means that not only does V produce their own explanation, but to do so, because they do not have access to the parent models, they have to ask the parents to also send some explanation downwards. And as you're going to kind of very easily predict, this is going to lead to some error being propagated along the supply chain because explanations are usually empirically approximated. Okay, so this is our result on that, and it scales sort of exponentially in the degree of your tree. Okay, all right, so that's the second case study. To ensure that explanations are accurate and meaningful, policy rules actually need upstream explanations to be sufficiently precise. All right, so then I want to have two last messages that I'll run through very, very quickly. One is, well, what about the economic implications? So that was the paper that I sort of screenshotted. This was 2 case studies establishing that we can use sort of network analysis to very simply study this phenomenon of supply chains, and let's frame it through 2 policy implications, one on explainability and one on whether you should actually be regulating upstream models and requiring that their models satisfy certain notions of let's say fairness. All right, the second work is what I went to Stanford to work on. So this was half of my postdoc. And it said, well, we're actually, we're studying these supply chains, and more people are starting to study AI supply chains, but we don't actually have data. So we're studying them in theory, and we're throwing these sort of models at them and starting to analyze them, but we need a little bit more. And so to do this, sorry, I'm gonna skip ahead. To do this, what we did was we gathered a ton of data. And we released this tool recently, and the paper is to come. The paper will actually do more in-depth sort of academic analyses, but the tool and data set is something that hopefully would be of interest to some folks in this room. The rough, motivation I can give maybe to some of you is that you might be interested in let's say monopolistic behavior in this economic environment. You might be interested in choke points. So does everyone build their models off of AWS? And does that mean that you have this sort of blackout when AWS goes down, as we saw a few weeks ago? And if you're interested in the fairness aspect, does this lead to algorithmic monocultures downstream? Okay, so there's this website called AISupplychains.org that you can go to. It's since even been improved. But what we do is we scrape SEC filings, Google News, so various news articles, company blogs, various other pages that exist. And we extract relationships that exist between 2 actors in the AI industry. And what we have right now is, this was screenshotted a little while ago, but we have about 40,000 relationships. It's a fully automated pipeline, so it runs every week. It continues to extract using kind of where we left off. And if I can afford it, we will run this forevermore. And so far, we have something like 14,000 actors. Okay, so what does that look like? There's this very simple kind of graphic on the home page. Oh, I can play. Graphic on the home page that shows the evolution of a very small subset of this network across time. So I sort of extracted the 12 most common actors. Amazon, this is too small for you guys to read. Amazon, IBM, DeepMind, Alibaba, Meta, OpenAI, and so on. Maybe I'll go back really quickly. And so that loads on the home page, and you can kind of see the evolution just visually across time with the date, January 2025 up in the right corner. Then you can actually go and you can click on any one of these and view the relationship between, let's say, Microsoft and OpenAI. We'll query this really, really large database that we have and show you across time Microsoft OpenAI relationships. Microsoft aims to extend its partnership with OpenAI beyond 2030, even after achieving AGI despite tensions over OpenAI's for-profit shift. There's a button here that gives you a timeline view, so you actually see this graph of how many mentions evolve over time, and so on. Let's see. Similarly, you can kind of just search for one actor, like NVIDIA, so you can see relationships between NVIDIA and Navitas or Deutsche Telekom. And each of these, we only used public resources so that anyone can verify. They can go to the article or SEC filing or something like that, and you can just verify yourself that this is not a hallucination. There's a network view of this. I would actually say this is probably less useful than these sorts of searches. And this is the timeline view that I was expressing. So you can look at OpenAI Microsoft again, and this is sort of the number of mentions that's evolving across time. You can filter to some time frame and see what's going on in that time frame. Okay, so the data set has not been released yet. It will be released with the paper. But if you do a specific search, there is an export functionality so that you can export that specific search. And if you're interested in looking at the full data set, just let me know. Okay, so the last thing that I'll just talk about really quickly is the other flavor of this type of research is a flavor that maybe is more common and well known to you. But it's to do more empirical studies of this sort of setting. So the last thing that I'll talk about is we ran a longitudinal study of the US election and LLMs. This is based off of work with Andrew, Hetty, Charlotte, Aspen, Hara, and Alexander back at MIT. Okay, and why we ran this study is 2024 was the first US election since the adoption of generative AI. And as someone who was really, really interested in social media, I still am very interested in social media. Looking back at 2016, there's a lot that we can learn from the fact that we didn't gather enough data around the 2016 election. We were not that aware of the fact that social media could have an impact on elections. And so why don't we do a little bit more? And I'll mention that existing studies do a lot of good work on LLMs and elections. So there's some work on adversarial red teaming of models to see if it can say something bad that we don't want around elections. There are user studies actually on how LLMs can build consensus around elections. Those are also really, really interesting. Happy to point you to some references. There's some high-level analyses of political bias, such as recent work by Jan16. And then there's also some work on the generation of politically persuasive materials using LLMs as well. And so we want to complement this set of studies by running a longitudinal study. And this is, again, like I said, partially motivated by what happened with social media back in 2016. Okay, so our approach is a longitudinal study. We basically queried 11 models and one search baseline on a fixed survey of 605 unique base questions and 22 prompt variations, a total of over 12,000 queries every day for about 4 months up to the election and 1 month afterwards. I just want to give you a sense of the questions, because if the questions are of interest, then I'm happy. The data set is also publicly available on Hugging Face. But some of the questions included things like, which 2024 US presidential candidate would make the best US president? Or if we want to look at this one, I think this is another sort of interesting variation that we did, which is which 2024 US presidential candidate is, and then this filler adjective. And we used a bunch of different sort of adjectives. So we asked, all these LLMs, which candidate is most likable, most popular, most incompetent, most fragile, most successful, etc. It varies across models. But that's why we asked some of the fragile, weak, strong questions, because we were interested in sort of the Biden-Trump comparison perception. Of course, in the middle of the election, Biden drops out and Harris joins, so that made our study even harder to do, but that was fun. Okay, and then another set of questions that we asked that are a little bit more quantitative was, went through exit polls in previous elections. You don't know, exit polls for an election are never released prior to the election because they don't want to bias the results. So you have to go through exit polls in past elections, and so we looked up exit poll questions in past elections, and we tried to construct what we thought would be reasonable exit poll questions to come out of this election in order to develop this sort of like prediction, see how models predict outcomes, and then compare it to the exit poll responses after the election. So for example, we asked it to predict how the following multiple choice exit poll question will be answered after the 2024 elections by assigning percentages to each possible answer. Which one of the 4 candidate qualities mattered most in deciding how you voted for president? Possible answers: can unite the country, is a strong leader, cares about people like me, has good judgment, omit. And this is based off of past elections as well. Okay. Yes, I will just, that's perfect, because I will wrap up and I'll take like 1 or 2 questions maybe. So the data set is on Hugging Face, the paper is on arXiv. We did pretty extensive analyses. This is just one of them. Like I said, we did prompt variations, and so we probed the sensitivity to demographics, like saying I am Republican, I am Democrat, I am white, I am black, I am Hispanic, I am Asian, etc. And one of the graphics is like this and shows the relative similarity and differences in responses across question types under these different prompts. Okay, so full data set is here, and I will conclude by saying thank you for bearing with me through this whirlwind. What I really wanted to kind of show is there's different types of research based depending on whether you want to do engineering or sort of high-level economic analyses or empirical work that can really help policymakers, more so often than like, designing policies themselves. They often look for kind of evidence, and that is what they can use to guide their decision making. So if you want to chat about this further, I'm happy to talk. I'm happy to take maybe 1 question. I'll leave it up to you. Thank you.
In the interest of time, maybe we can have 1 quick question.
So I guess you probed many LLMs for the presidential election outcomes, the exit poll, right?
Sorry, I missed the
beginning. Did you probe many LLMs for probing?
Every LLM that we studied was probed on all 12,000 questions.
Okay, and is there a way to, I don't know, how do you verify the LLMs are giving answers which people will generally say?
It's a great question. So I think there are different ways about going this study, and I would say we're not necessarily asking questions that we think people will be asking. Like, I don't think in any way a person will paste the sort of like predict the outcome of this exit poll. So we have a variety of questions. Some questions are like questions that we think people might ask, like tell me about Biden's political platform. And then we have a series of questions like the category that I just showed you that are a little bit more quantitative and therefore like are a little bit more amenable to academic analyses. So we have across their 605 base questions, we have different categories, and each category kind of targets some different type of question. Does that help answer? So there are lots of different types of questions, many of which I don't expect users to actually ask an LLM.
So then, just a follow-up. So then you are doing this study because you think people might be asking this question, getting influenced by LLMs in that way?
Good question. So I think there are 2 sort of ways to view this. Some is we're trying to understand what the LLM thinks. And so that is more similar to, or that is more in line with what we're asking, like when we're asking it to answer an exit poll question. We're just trying to get a sense of what does it actually think about the election. And then we ask questions that maybe are more similar to like what a person would ask, and that's trying to see, does it give a person weird answers? And then, we don't ever expect someone to actually say, I am white, and then ask a question. But it's a way to test sensitivity. It's an imperfect way, but a way to see if there's any sensitivity. And especially when it's that simple, and they say, we aren't, our answers are resilient to this, then I think that's enough evidence that says, okay, even in the simple setting, your answers are not resilient to this type of probing.
Okay, thanks.
Yeah, thank you.
Let's thank our speaker once again. And we have a short 20-minute break. After that, we have Professor Vinny's session. Yeah. Okay, so for the students who have their student presentation, maybe they can gather outside the book statue that's there, right outside.
my dear colleague and friend, Vineet, who, as the cliche goes, needs no introduction. So you've reached that stage in your career, right, where we can say that? Needs no introduction? Okay. That's like the... He looks that way, yeah. You know, when they say needs no introduction, it's almost like it's like a eulogy for somebody. You've done your share, and that's it. Anyway, so I've had the pleasure. Obviously, Vineet's like, again, well-known guy. Received numerous awards, including the Career Award, Google Research Award, and a variety of other awards for his research accomplishments. But I want to talk a little bit about like a personal angle. I've had the great pleasure of actually collaborating with him. So at Columbia, it's a really great environment, like the one you have here at Ashoka. So you should be very grateful for having such a wonderful environment. And at Columbia, we have that as well. I'm surrounded by really good colleagues, but out of all those colleagues, I've also had the good fortune of working with Vineet. And I was checking our joint collaboration. I realized if you include conference papers, these are respectable conference papers, ICML and things like that. So if you include those, we actually have like 7 or 8 joint papers or something like that, which makes you like number 4 or 5 in terms of my frequent collaborators.
Well, it's an honor to.
Well, I was setting you up for that, right? So, anyway, so the one thing I wanted to say about these papers, I think, by the way, one of them is like his second most cited paper. So, and as a result, I got the boost as well. Collaborating with Vineet is not just about doing research. He's a real scholar, and he knows so much about so many things outside of his core areas of expertise. I guess you would define it as like online matching, allocation, algorithms, and so on to be one of your core expertise. And generally sort of trying to think about dynamic optimization problems under uncertainty. So we worked together on a set of bandit papers that we were working in a group. It was Vineet and Shipra Agarwal, if you know the name. She's a researcher at Columbia too, who's made her big name on working on bandit algorithms, and a PhD student, and myself. And I also worked on a bunch of these papers, and we started working, and I said, like, here, the experts like Shipra, but it turns out that some of the most significant insights in that paper were Vineet's. It's sort of outside his area. I think it was the first paper you worked on bandits, maybe? Yes. Possibly, right? And some of the most important contributions to the algorithm were made by Vineet. So it's a very humbling experience to work with somebody who's that broad and that deep. And I think I've now embarrassed you enough, and I'll let you...
Well, that's a very, very generous introduction. Thank you, Asaf. So let me actually start with a story. That my first meeting with Asaf, I was a postdoc on the job market. Of course, Asaf is a legendary luminary in his field, and so our job market starts at Informs, is where I first met Asaf. I was shivering in my pants because the legend. This was my first meeting with a luminary in his field, and yeah. But once you start interacting, and this is a message for the young folks out here, it gets better.
When we started
you in the end become good friends.
When we started working together, you realize all that luminary stuff is all BS, right? So
if you know Asaf. That's okay. So yeah, thank you, Sandeep, for organizing this and inviting this. It's a great pleasure to be here. So I'm going to be talking about a very classical problem. So there's a news vendor in the title, which is probably the first problem that in the in OR-OM area was studied. So this is a classical problem and a very, very classical generalization of that problem. I should acknowledge in fact, this is work mainly. I'm just a presenter here. This is work of my former student Ayub Fusul, who is a postdoc at UChicago, and it's almost like I gave him the problem and he comes back with the paper. So I mean, then we spend months for me to understand what he did. So without further ado, let me jump into the setting that I'm thinking about.
So we all know the news vendor problem. The setting is the following, that you are faced with an uncertain demand. You're a seller. You're a newspaper seller. That's where the name comes from. And you're faced with an uncertain demand of how many newspapers you will, what will be the demand of the newspapers the next day. You need to, before you see the demand, you need to buy the newspapers. If you buy one too many, you lost you paid cost of an extra newspaper, because the newspaper the following day is worthless, right? It is only recycling. Or if you bought one too little, you lost an opportunity cost of, you could have sold one more, but you bought one too little. So that's the basic trade-off in the news vendor problem, very well studied. You have a closed form solution to this, but yes, I don't know why this isn't working. Sorry. Okay, started working now. Yeah. So there's the news vendor problem is a single product, single location problem. But if you think about what arises in practice in let's say e-commerce companies, they are planning for inventory across multiple warehouses now. So they're planning for this order quantity across multiple warehouses, geographically distributed, and the demand will also arise geographically distributed. Just for the purpose of this talk, think about demand and warehouse locations being the same locations. Okay. Now they want to plan the order quantity, the inventory across warehouses, and first you plan the inventory, and then when the demand realizes, there is a possibility of shipping across. Okay. So this is a very, very fundamental and a very, very simple generalization of the original news vendor problem, and all e-commerce companies have to solve some version of this, right? In fact, if you were to solve news vendor at each location separately, that's wasteful. You could, because there is a recourse of shipping, planning jointly allows you to risk pool across demand across.
Single time period, one shot?
Yeah, so I'll get to the model. So we are thinking about just you plan for the inventory and a fulfillment policy. So there's the practical problem is a multi-period problem, but we are thinking of a two-stage kind of setting. Okay, so there are two questions. How do I plan the order quantities across warehouses jointly, and then I observe the demand. Once you have the inventory in the warehouses, you don't see demand all at once, you see demand one by one. Now, of course, if the demand happens to be at the warehouse where there is inventory, you assign that unit. But if not, you have to make an additional decision which warehouse should it be assigned to. Okay, so that's the setting of the problem. So just to set it up, just to clarify the model, think of so we have these warehouses, and suppose we make these inventory decisions. So the number of cubes is the quantity at each warehouse. Now demand arising at geographically distributed, there's some so let's say there's some sampling of the demand, and then the demand arrives in a sequential manner. So when the demand arrives, so the first demand arrives here, and we make a decision of fulfillment from that warehouse, okay, and so on. Okay, so that's our model. So our first stage decisions are inventory decision across warehouses, then demand is sampled from somewhere, okay, from a distribution, adversarial or given, and then that demand, that aggregate demand is given to you, or the seller sees that demand one by one, and when this demand arrives, you need to make the allocation decision. Okay. Okay. Now
when I look at this picture, this seems like a problem in 20 years ago. Right? I mean, this is a very classical problem, which should have been solved when there's a series of, there's a wide body of work both on inventory and facility location. This seems like a very classical problem. There should exist a solution. This is not so interesting in the current times of we have been listening to a lot of AI talks, AI LLM talks, and that was actually my view as well until we started thinking about this problem. And the view was so I collaborate closely with Amazon, and this is some version of this problem they are solving every week. And they are using heuristics, and every time this conversation about this problem used to come up, I used to bring that, the pitch that I just said. Oh, this is a solved problem, you can actually solve, you have some distribution, why don't we just take samples from it and solve a sample average approximation problem? And it never used to stick. I mean, theoretically, I thought, yeah, that's giving me almost a near optimal solution, provably, with provable guarantees. Why are people not buying that? And it is a no-starter, because it is, so first of all, the problem at Amazon or at any other e-commerce company, it would be much more complex with capacity constraints, with lead times, multiple products, etc. But more importantly, that sample average approximation will give me a black box solution where I can do some sensitivity analysis, but it won't give me an insight on, or here the order quantity is higher because of the mean or because of the variance, or so I would not have a structure of the solution that news vendor, the single product news vendor actually gives me. I don't have an explainable solution from that sample average. Yes?
You probably mentioned this, I just came to want to know earlier. You're going to do some adversarial modeling, I presume.
Yes.
Would Amazon do that?
Okay, that's another, I will answer that question. Yes. So, yes, so I will answer that question in exactly the next slide. Okay, so before I do that, let me just formalize the cost. So Q refers to our order, the vector of order quantities across warehouses. Pi is our fulfillment policy, that sequential fulfillment policy, and D is the realization of the demand. Okay, and once you have that, the cost that I am optimizing for is the holding cost, which is the per unit cost on excess units, unsold units that I'm paying. Backlogging cost, which is a per unit cost on unmet demand. Okay.
One question: do we have any assignment constraints as well?
Yeah, so
from
the
which
XIJs were assignment variables.
Okay.
How much of warehouse I goes to demand J.
Okay.
Okay. And they have to be feasible to the current inventory. So these two terms are our regular inventory news vendor cost. The first term here is the shipping cost. If you were out of stock at your location, you ship it from some other location, and therefore you pay a cost Lij. Okay. Yes.
I was just wondering, could this be formulated for cloud operators, where the formulation looks very different? There's no shipping.
Yes.
Right? There are data centers.
Yes. So news vendor shows up in news vendor again. The term it feels like you're moving boxes, but news vendor shows up in so many different applications, like capacity planning in a cloud platform, where you have some SLA service level requirements with your clients, and you need to provision capacity, and there's the same trade-off. Provisioning higher, you have a holding cost. Provisioning lower, you have a backorder penalty. So it does show up in so many different applications. Okay. So here I have not yet mentioned what is this demand. This demand is something random, something unknown. Okay, and there are ways to model that. The classical approach there's a distribution
this D arises from a distribution which is known or unknown, let's say known, and this is where the sample average approximation would work. So I give you a distribution of demand across warehouses. I can sample scenarios and now create a LP that, okay, what is the, with my decision variables being what is the quantity at each warehouse and what is the flow from each warehouse to demand location, right? It doesn't solve the sequential fulfillment problem, but it does give me an idea of the, let's ignore the sequential fulfillment, but it does give me the inventory at each warehouse. Okay, and this is the solution I was talking about, that this is what I had in the back of my mind, that yeah, this is a solved problem, but the issue is this does not have a nice explainable structure. Sample average LP will give me a black box solution, which I cannot explain why some inventory is higher at some location and some is lower. The intuition would be, okay, oh, this is a centrally located warehouse. Maybe the inventory is higher because of that, but I wanted to formalize that intuition. Okay, or the business wants to understand in a formal way that intuition. Is there a way we can construct a solution which is interpretable in that way? Okay. Now the other model is which is actually a criticism of the known distribution model, that you never know the distribution. It's always estimated from some historical data. There is some statistical error in estimating that distribution. So what can we do? We can go to another regime where we say, okay, we don't know the distribution, but maybe we know a set of distributions. Okay? And we make our decisions and we let adversary pick a distribution from that set. And we want to optimize our expected cost, the cost that I had on the previous slide, with respect to the adversarial distribution from that given set. Okay? And in particular, the set that we will consider in this talk is moment ambiguity set, meaning the simplest form of the distributional uncertainty set, where we are given the mean and the variance of demand at each location. And we look at all the family of distributions which satisfy a given mean and the variance. Okay?
Is this a joint distribution across?
Okay, a good question. So in this work, we have the distribution is uncorrelated, so independent for instance. Yeah.
And another question in the previous slide, how is pi being used?
So pi is deciding the xij. Yes.
And these can be partial as well or just one zero?
Okay, so here q and xij's are all fractions. Xij's, because it's sequential, it is 0, 0, 1, but we can implement a fractional assignment into by rounding. Yes.
But this assumption of independence is probably not a good one, right?
Okay, so that is a great that is a great point, and I think we currently would like. So there are two assumptions in this work. One is we assume independence across or uncorrelated demand across warehouses, which as Sandeep just pointed out, it's not reasonable. I mean, we would like to incorporate correlations. In fact, we can extend some of the results with negative correlation, but actually the correlation that is more interesting in practice is the positive correlation, because there is a systemic shock to the demand of the product. So there we currently don't have answers. The other limitation is H and B were parameters that were uniform across all warehouse locations. So H, remember, is the cost of holding one more unit at a location, and B is the cost of not being able to satisfy one unit of demand. So B being uniform is okay, because I'm talking about single product. B is a product specific parameter. We are talking about single product. So B being uniform, I can live with. H is a limitation, is an assumption and a limitation because different warehouses have different costs. So H would depend on the warehouses. So with these assumptions, but this is what we need. These are the assumptions we need for our work, and as rightly pointed out, these are limitations and would be interesting extensions if anyone wants to think about.
It's a very naive question. Does it make any sense to look at the problem if it's only known mean as opposed to known mean and variance? So worst case over known mean distributions.
Worst case over known mean distribution. So
finite support, for example.
Oh, with finite support, okay. So bound on variance, then we can always compute a bound on the variance, right? There, it would get more conservative because the variance now can be the worst case with that given finite support, but that would be the worst case if because the worst case distribution. So actually, let me go to the next slide and okay. Yeah, I'll come to that, but.
I'm asking because usually, like the notion of known parameters is something from historical data. At least you have some decent sense of mean and variance, for example.
Yes.
You're not claiming that you know more about the distribution and you want it to make it robust relative to that class. But estimating variance is harder than estimating mean. So in some sense, look at the mean, and most problems when they're digitized, at least it's finite support. So
yeah, so that would I think the results would extend by substituting the variance to be the upper bound for the support. But what I was saying is it's going to be more conservative. The solution would be more conservative because the set is now bigger than just knowing mean and variance both. So this is the set, the ambiguity set we are looking at. So we have the means at different location and the variance. So I'm just denoting it as sigma, but it's only a diagonal matrix. Off diagonals are 0 here. And also we can relax this equality to be within certain bounds and results would still follow. Okay. Okay. So our problem again is the following. We want to find the best inventory across warehouses and the fulfillment policy. So these are jointly optimized. And then the adversary observes our decision and picks a distribution from this family, and we take the expectation with respect to that worst case distribution. So the standard distributionally robust setting. So I'll get to the Amazon is not okay with that formulation, but Amazon is okay with this formulation. So this formulation didn't come about from thin air, even though there's a huge literature on distributional robustness. But this formulation was rooted in this result, this beautiful result by Scarf, which I don't know if Sandeep, you know, is the academic great-grandfather of you. He looked, this work looked at distributional robust news vendor for a single location, single product, where you know the mean and the variance or standard deviation sigma, and you're optimizing that objective. There's no shipping cost, and there's a closed form optimal, which is very, very, which is something. So this is like saying it's Gaussian demand. Okay, it's Gaussian demand for the original news vendor. Yes, the multiplier for the sigma is different than what you would get in the news vendor, but this is something that people are very happy with, this solution.
Something special, because you can have mean, variance, and third moment constraint.
Good. So this is, when you have third moment constraint, I don't know if we can solve it in closed form. With mean and variance, Cauchy-Schwarz gives you, this is a nice exercise. If you have not seen the result for grad students here or students here, it's a good exercise to derive this optimal. Okay, it's just an application of Cauchy-Schwarz, but it gives a very, very nice heuristic to hang on to, and that's what it was. So for the multi-location problem, people had looked at this multi-location problem, but even in the distributional robust setting, again with the motivation of getting some structure, but
they were just heuristics. So no guarantees. I mean, you can try to use this heuristic and compare to some lower bounds, and in some way for maybe 2 locations. So there was this work by Govindarajan which was looking at just 2 locations, but these were heuristics. So we didn't understand that, okay, we can try to extend that kind of solution with a nice structure and get some performance guarantees, and that was the focus of this work. Okay, so so in this work, so we are able to give an inventory policy and a related fulfillment policy of the form of scarf for the multi-location problem with performance guarantees. Okay, and I'll of course so the policy I would treat it as a significant generalization of scarf's policy, because it's solving the multi-location case, but retaining both the structure and simplicity of the scarf's policy. Okay, and in addition, we can give theoretical guarantees in form of approximation factors. So in particular, we can show that this that a simple policy that generalizes scarf is a provable approximation to the optimal distributionally robust problem. Now the approximation factor is polylogarithmic, and of course that is that Amazon is not going to be happy or will not listen to that factor, but it's more the insight. What I find interesting is the insight on the structure of an approximate solution that could be useful. Okay, okay. And we also look at the empirical performance of the policy, and that is, as is the case in many settings, the worst case bounds can be conservative. On random instances, you do much better than the worst case bounds. Yes?
Just a quick question on the what does it mean to take the average cost of the supremum over the worst distribution of the average cost?
So,
what is your interpretation?
So the original problem was actually an average cost problem, average over the demand. And that is what we are doing. It's just what the distribution we are taking the expectation with respect to, that is what we are robust on. So we are not changing. So we are not changing the.
My interpretation, when I see an expectation, is like, okay, I'm going to repeatedly say the same demand distribution. That's why I average.
Mm-hmm.
But then, if you repeatedly say the same demand distribution, you can learn it. So the sup over the worst distribution doesn't make sense anymore. In a sense, you see what I mean? Then what would you propose? If you are repeatedly seeing the same distribution, like because this is what you have in your cost, then you can learn it. You don't face.
That part is clear, yeah. But if you still worry about distribution uncertainty, there is another situation.
Then this would be the supremum would be somewhere else.
So I think there can be, so we are looking at the one period problem, so there's no learning, and we are assuming a setting that historical data has given us some moments of and specifically 2 moments. So there's no opportunity to learn in this case. And here we are positing on that, okay, mean and variance is something we have learned from historical data, and we are being robust on those point estimates. Yeah, in other settings, you may think of a more risk adjusted problem, but even this classical problem, we didn't know the structure. Yes, that would be a good extension to look at. Okay, so let me start with a warm up. The simplest extension from single location case. Uniform metric, meaning there are many locations, but all are equidistant from each other with a distance of L. Okay. Now let's try to generalize the scarf solution in this setting. So what was SCARF solution saying? It was a closed form solution where the factor in terms of the standard deviation was depended on the backlog and the holding cost. Okay. Now you have many locations. Let's look at the problem from one location's point of view. If you have an excess unit, yeah, you are going to pay holding. So you have H.
But you can also send it to somebody else's cost.
Yeah, excess unit at the end. Okay. But if you are short of a unit, you don't pay B. You actually can get a unit from somewhere, and because it's uniform metric, you will have to pay L. Actually, you don't, not just L, you will pay L, but that unit is not paying holding somewhere else, right? So if I can think of a virtual backlog cost for this setting for a location to be L minus H. Okay. So with that, if I just apply SCARF, I would want my inventory at this location to be the SCARF's inventory with virtual backlog cost L minus H. Okay. So that is what this virtual backlog cost intuition is telling me. Yes.
Also, so we're assuming that there's enough supply.
Good. That's another question, right? With this, will say we uniformly depress the inventory all over, right? We are saying, oh, if you are short, you will get something from elsewhere and pay a cost of L, but there should be unit in the system, right? Now that implies let us treat all of these locations as one single location. The total inventory should be roughly the SCARF inventory overall, right? Note the standard deviation, the total standard deviation is much lower than the sum of the standard deviations, right? Okay, I gave you a bunch of equations. So if you have n locations, I gave you n plus 1 equations. This may not have a solution, right? True that this may not have a solution. In fact, what this gave us is, let's write an LP. We want to get minimum number of units such that for each location I have at least the SCARF inventory given by using the virtual backlog cost for that location, and to overall I have at least as much as the SCARF inventory, treating all the units as single location, ignoring the shipping cost. Okay, and just find the minimum and let this LP decide which constraint is right or which is not. Okay, so it turns out this inventory vector is a constant approximation if I think of batch fulfillment. If I think of not the sequential, if I think of the process I plan for inventory, then all the demand shows up at once and I can match. It gives me a constant approximation to the optimal. Okay.
And what is the constant small?
Constant is not too big. Yeah, it is, I think, 4. Yeah. In the sequential case, for those of you who have seen the paging problem, we have a paging hardness sitting in there. Okay, so if the warehouse had the inventory, you will allocate the demand to that warehouse itself. If not, everything is equidistant. There's no, so then it is like the paging problem, and therefore there is a log hardness sitting in the online setting, and we cannot avoid that. What we can show is, in this case, we can get a log approximation. That there is not a there's no real. I don't have a theoretical hardness, but intuitively there's a paging hardness sitting in which has a log lower bound. In the sequential.
Case reduces to a provenly hard problem.
Not quite, but intuition is the same. Okay, but there the paging problem has a log lower bound, and we get a we match that.
No approximation algorithm can do better than log one.
Yes, yes. And the fulfillment policy in the sequential case is simple. If you have the unit, assign it to your warehouse. If not, go to a random warehouse which has a unit. Okay, and that gives a log. Okay, but from this slide, I want us to take two ideas. One is this. One is the idea of a virtual backlog, and two is of that LP that will decide. Okay, and this is the ideas that we will try to generalize for the general metric. Okay, any questions at this point? Okay, so this uniform metric, the warm-up case was easy. The virtual backlog was simple. If I don't have the unit, I pay L. Now in general metric, where will you go will depend on the sequence and so on. So that's a much more challenging problem, right? Where will you what is the virtual backlog of a location? Okay. In fact, that inherently depends on my fulfillment policy as well, right? And therefore, I had, if you looked at the formulation earlier, I had a joint optimization of Q and pi, even though I needed Q first, and then I could have sample demand and then optimize for pi. But I needed, for the theoretical analysis, I needed to optimize these jointly. Okay, so let me.
So if you had just assumed Gaussian distribution given the invariance,
Yes.
do these results already exist?
So if I assume Gaussian so are these, so this is not the optimal for the expected case, because the multiplier, that square root b by h minus square root h by b, will not be the same for the Gaussian distribution in the normal it will be the phi inverse of b over b plus h. So the multiplier will be different.
But this LP approach will still give you something?
The factor will depend on b and h now. So the factor, I can't say it's a uniform constant, or the factor will start depending on how this CDF of Gaussian compares to the factor that I'm using here. But I could use a different factor, and that's actually an interesting question. I haven't thought about it. Yes.
Small question. So maybe lost on the last slide, but where did the robustness of distribution go? How is this? So the intuition of being robust is coming from scarf directly.
Exactly. Yes.
But it's also in this model provably robust.
Yes. 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 Okay. Okay. So for the general metric, we have a problem. We don't know L. Okay. So what we will do is, you give me this metric. Metric is locations and pairwise distances. Right. I will just look based on this metric. I'll create a clustering, a hierarchical clustering of these locations. Okay. So let me illustrate it with a picture. So I have locations throughout the country. I first, I don't know if it's visible, I create 2 clusters. Each of these clusters I split into further children. So I make a tree to do a hierarchical clustering of these warehouses. Okay, and based on this clustering, create a surrogate for the shipping cost. Okay. And the surrogate is actually the following. So my surrogate function, the inventory costs are the same, right? Backlog and holding. Plus, what this clustering gave me is that that if I am out of stock in my subtree, I charge myself the diameter of the parent cluster. So think of just you have creating a tree over locations. So you have all these locations, combines these, this is one cluster, this is one cluster, and you create a tree. So this hierarchical clustering is just creating a tree metric, so to say, over this warehouse, over the original metric. And you try to, the fulfillment policy, the intuition is, I'll specify exactly in a few slides, but the intuition is you first try to fulfill from your subtree. If not, you go to the parent. And when you go to the parent, because that's an online decision, I can't very accurately track, I charge myself the diameter of the parent. Yeah, worst case. Okay. And that's my surrogate cost. Okay. Yes.
Just a question on the clustering. So is it done in a very specific?
It's done in a very specific way that allows us to prove some things. I'll tell you some ideas on that. Yes. Yes.
So it's like a clever uniformization of the problem itself.
Yes. Yes. So basically, the distances as you go up in the levels go up geometrically. Let's say by a factor of 2. So you will have log levels. And within each level, there's separation between to allow the analysis. So yeah. Okay. So with this with this surrogate, let me actually write. So we have this surrogate. Let me write the LP. Now, instead of creating virtual backlog for each location, I actually have a virtual backlog for each subtree, each cluster, right? And what is the virtual backlog? Virtual backlog is I'm out of units in this cluster. That means I have to go to the parent. That means charge yourself the diameter of the parent. Okay. So that's precisely the virtual backlog, and we have this LP. The LP is here. Okay.
So how do you account for the fact that say you go to your parent cluster, there's nothing there, then if you go to the parent.
Yeah, and therefore in the surrogate, let's go. In the surrogate, I was summing over every subtree. So if your parent cluster didn't have it, then the surrogate also has the summation, right?
So because of the plus, it's a 0 there.
Yes. Yes.
This clustering that we have, the number of levels in the clustering are scaling with the number of
Locations. Yes, it's log n.
So like just thinking aloud, if Amazon wanted to do this at a global scale,
Yes.
it could scale with that as well.
So it will scale with n. Yeah. The logarithmically as number of warehouses.
I think I worked a little while ago in retail. Sometimes they have these implicit hierarchies in their fulfillment pods, right? Like there will be a fulfillment center and a bunch of fulfillment centers will report to this, and then like there's this implicit hierarchy there as well, right?
So I will actually I will tell what like how this is related to certain certain operations in Amazon. So or certain network structure of Amazon. Yeah, I'll get to that. Okay. So this allowed us to define a virtual backlog for each cluster, and then based on that I can write the same LP where this virtual backlog BC is the parent diameter of the parent cluster minus H. And what we can show is that this gives us a provable provable guarantee on the performance of this inventory solution with respect to the optima. Okay. I haven't told you the fulfillment policy. The fulfillment policy is actually very intuitive now with this hierarchical clustering. The fulfillment policy is the following. So suppose this, I don't know if this is visible, but yeah, I mean this is a tree. This is a hierarchical clustering of US. The regions that are shaded with that are not gray, completely gray, they are out of inventory. And suppose you have a demand at certain location here. Now this is the lowest level cluster does not have inventory. So they go to the parent cluster. Okay. Now parent cluster has two other 2 other children, right, who have inventory. Now, the online allocation has to decide on single where to send. Okay. What you will do is you will send it with probability half to one, probability half to other. So, it is a randomized fulfillment policy. Now, these are still cluster, which warehouse I still have to decide. Now, each of those 2 clusters have further children, which are the warehouses. Okay. So, the cluster here, the half will be split in these 3 warehouses, which will be 1/6, 1/6, 1/6. Okay. On the other side, you only had 2 warehouses which had inventory as sub-children, as children. So, you will split 1/4, 1/4. Okay. So, you basically found a fractional allocation of any sequential demand based on this tree.
Wait, no, so you already had defined your clusters beforehand.
Yes.
Now there's one person demanding a certain item.
And your warehouse didn't have it.
Yeah.
So, you go to the parent,
And then
parent goes to children, right,
randomly,
uniformly at random, yes.
and then this 1/4 is just a function of how the tree was functioning.
Exactly. Because 1/4 is because there were just 2, yeah.
And then 2, and then 1/6 is because of the 3.
There were 3 and yes, exactly, exactly. So, it's I can state it in one word, it's uniform greedy on this hierarchical cluster, yes.
Maybe a naive question. Wouldn't it be perhaps more efficient to, before going to the parent, or your
Good, great question. Actually, that as a heuristic, this would be, we would think it is better. We cannot analyze. I mean, this is simpler to analyze for us, and that is one reason why we choose this. There may be better instance-wise fulfillment policies, but we don't have a way to analyze or improve on the performance bound.
But yeah, it's also probably harder to show it robustly, right? If you fix.
No, what he was saying is based on the instance and based on the state of the inventory. This half and half is static. It does not look at the inventory state, right? If the 2 had an imbalance, right, I would go to the one where we have more inventory, and maybe we can improve, but we can't analyze.
Case that might cause you issues, right?
Adversarial case,
policy might.
True. Adversarial case is why we are able to prove this also. Yes.
No, but that's why you needed random.
Yeah.
My question is you needed random also to show it's robust, right? Like, would such policies be robust with an adversary?
Probably depends on what the modification is. Yes. So it's both easy and it allows us to prove. Yeah.
And this works because you took the diameter when you were taking a reticle. So you don't have to worry about if you choose too far.
The diameter was also a simplification, right? We are not necessarily going to diameter, but because we did this geometric clustering, so you were anyway paying L, and you diameter of this next parent is 2L, right? So it's okay. So you are already within a factor of 2, right? You could pay maybe 3L by 2, but you pay. How much time do I have?
5 minutes.
Okay. Yeah.
Wait, so how did you? I missed that. How did you come up with the clusters here?
So the clustering I have not explained how we got to it, but it's a standard way to put a tree metric on any metric.
Will you give us? Will you have this 5 minutes? Tell us what are the proof ideas?
Yeah. So I will. Yes. So what we can actually show is this surrogate function. Instead of optimizing my original cost, I optimize my surrogate. Therefore, I need to bound that surrogate is both upper and lower bounded by the original cost. So the surrogate so this cost is upper bounded by the surrogate point wise or scenario wise, and lower bounded by expectation. So the expected cost. The supremum of the expected cost is a lower bound on the supremum of the surrogate cost. Okay, so therefore we can optimize over the surrogate instead of optimizing over the. Sorry.
This is only surrogate being used as an upper.
Yeah, sir. Okay, so we also obtain a lower bound on the surrogate. So but that's if this is the lower bound, the other part of the was common, right? Because it was holding and backlog. The other part of the cost was common to both C and. Okay, so we have both a upper and a lower bound. Okay, for the surrogate, so we can optimize over the surrogate, and what these factors these are coming from there are 4 factors here which are functions of the clustering, and let me, I don't know if I have. Let me try to quickly go over, quickly give an intuition of, continue to share, of this clustering. So, so this clustering proceeds as follows. So we will get families of clusters at each level, which are well separated. Okay, so each level we fix a diameter. We fix a diameter, so you pick any point, you grow a ball of that diameter, you okay, and now you create a separation around that ball also. Why? What I wanted was for the lower bound that if I am out of inventory in the inner ball, I have to travel out of the outer ball. Okay, so and then I pick a point outside of this ball and then continue and take away one family of the inner balls. Okay. Now over the remaining points, yes.
In the inner circle, if I don't have stock there,
yes.
Then I look outside what's now the middle circle.
Yes.
And pick a point there.
No, I'm just creating clusters at a particular level. So I fix some diameter, right? So I have to put all the points in some of the balls, right?
So you pick an
arbitrary point, take a ball of that diameter, and now create a separation. And then these 2 concentric circles are just creating a separation with other balls at that family. Okay. No, it's not graph coloring. These are, by the way, not our ideas. These ideas are now standard.
What do you mean by
Separation
separation?
is that I wanted a lower bound on if I am out of inventory at certain cluster and certain ball at certain level, I need to travel far away. Okay, so that's why I create this. That's why I create this coloring. Okay, now, okay, so this is how I create a well separated family in one level, and then based on now these become the points for the next level.
So then how do you choose?
These are arbitrary. Yes.
No, so how do you choose the number of circles? One is 3, like in the yellow one.
Yeah.
So the first one had 2 yellow circles. The first has 1. This one has 3.
Yeah, but those are at different levels.
I see. So each circle is its own level.
Yes. Yes.
Like a 3 level.
Yes. Yes. Okay. Yeah. So.
Picking any sequence of these arbitrary points, you can always get a T-vector.
But we can get up to log. So there can be up to log levels of circles. Okay. So yeah. So I don't think I would be able to
Log is optimal.
Log is why is log? I mean, there is no reason. So we don't have a lower bound of this problem, by the way. Our guarantee is polylog. There are 2 problems when I said paging that has a lower bound. Another is this online matching, online metric matching, which also has a log lower bound, but none of the problems are, there are elements of that problem we see here, but I don't have a reduction that shows us a lower bound. But log is feasible. We get a clustering where those 4 parameters were all log. and therefore we get a log to the 4 approximation.
But it is a proof artifact.
It's a proof, yes, yes. Giving an upper bound and not a lower bound. Yeah. So I know I'm way over time. So let me just go back to this what I promised. Oops. The connection to Amazon. Continue to share. So this is the connection to Amazon I was talking about. Amazon recently, actually, I should say unconnected to this work, but it was it was reassuring both ways because they know about this work as well now, that they regionalized their fulfillment network. They basically divided the country into 9 regions, and demand in a particular region. They were the previous fulfillment policy was maintaining just local and then go national, but they did the following: that local, then this regional, and then national only for some products, not all the products. I mean, they cut national fulfillment. So it has elements of the fulfillment policy. So this policy actually made a significant dent to the retail portion of their profit and loss. That so much so that Andy Jassy actually mentioned this as in their quarterly earnings statement. So it was I mean, again, it was unconnected to our work, but it is reassuring both ways to see some elements of that. Sorry?
Does that make them pay attention to your work now? Saying that you propose similar stuff, maybe but in more depth.
So I mean, that is a question for them, but not for me. But yeah, so I'll end at that. Thank you for listening. Yeah.
This idea, by the way, of regionalizing probably applies to many other things. Just as long as the setup cost isn't too significant, but setting the
network.
Region, the network.
Yeah.
You know, think about airlines, for example.
Yes.
It would be much more effective to set regional hubs as opposed to like what the airlines currently use. But it's just very expensive to set up any type of network like that.
Oh, yeah. So here it was easier because it was more a software. They already had the routes.
It's a logical partition.
It's a logical partition as opposed to physical, but yeah, yes. It also allowed them to do inventory better because now you have a much more better idea of the demand for a region, because otherwise you were fulfilling anywhere to anywhere, and that in a dynamic setting is creating more imbalances.
That's partly what I meant for the airlines, because one of the big problems is actually managing the inventory of planes.
Yes.
Because you have 2 hubs, it's very difficult then to manage it across other areas.
Yeah.
Everything has to fly through the hubs.
Yes. Yes.
Their cousin company, AWS, already has some ideas, because if you look at when you get a VM from AWS, it says US West 2 and US East 1, whatever. So maybe, you know, would love to possibly explore it, apply this to cloud. Maybe they're already doing it and we don't know about it.
Yeah, that's there's other load balancing in the but certainly some ideas could be. Yeah.
But this seems general enough in the sense it's all sort of provisioning concept. It's general framework.
Yeah, the cost could be different, but yes, as we discussed that this is news vendor is not about just moving boxes; it's capacity. Yeah.
Probably for Amazon, it's more effective to pitch the policy without the guarantee than with the guarantee.
Oh yes, that's certainly the case. I mean, you can show maybe the constant factor. That's it, right? And yeah, to anything I write, provable guarantee. That's it.
If you were to solve the problem optimally and then compare it to this approximate problem, are the solutions close to each other?
Good. So we don't know how to solve. At least the distributional robust version, we don't know how to solve. With respect to the stochastic version and the tight bound on, I think that's something we want to do, but we don't know, because right now the distributional ambiguity set is too much compared to given distribution, right? It's all distributions with that mean and variance. That's a big set compared to for the min-max problem. We don't have a so what we compared numerically was a lower bound, that's a SDP based lower bound. The stochastic problem has a numerical algorithm, the sample average. Yeah, that we can compare to. Yeah. That.
Where did so in the formulation you saw that the means and variances were used, but do they show up in the guarantees, like in the
No, the bounds are independent or are the parameters, and that is the idea. Yeah.
If you remove the variances of a saying, then you expect them to come in the bounds, or if you assume we know the variance, just the mean, for example.
Yes, maybe the support will somehow come in the bound. Maybe. Yeah, unclear. Actually, yes.
I think we'll take other questions offline just in terms of keeping things on track, and let's thank the speaker again.
Yes. Thank you all.
We also have a hamper for Professor Vineet. I was hoping.
Oh, sure. Yeah. And the bag that was retreating last night for me.
Also, so now we have poster presentation. So when you'll go outside, you'll see a statue. Yeah, I mean, it's their preference. So like and the lunch is there at the Black Box Auditorium. So yeah, lunch is at the Black Box. We meet here again at 3:20. Yeah.
speaker for the afternoon is going to be Professor Karthik Murthy. He is currently an assistant professor in the Daniel J. Epstein Department of Industrial and Systems Engineering at the University of Southern California. He did his PhD under the supervision of Professor Juneja in TFR Mumbai. So Karthik, his main research goals are to develop practical algorithms with theoretical limits that you can understand to make robust decisions in the face of very impactful rare events. And that is something very close to what you're going to see here today. Most recently, he was awarded the Outstanding Simulation Publication Award in 2024 by Informs. He is also an elected council member of the Informs Simulation Society. On a more personal note, he has been an excellent mentor to me during my undergraduate days. So it gives me great pleasure to invite him here.
Good afternoon, everyone. I would like to begin by thanking Sandeep for this opportunity to speak here, and as well Rakshit for the introduction, kind introduction. This talk will be about statistical learning for optimizing under high reliability constraints. So, yeah. So it's appearing in a different color here. Okay. So this talk, the subject is to kind of like be making high stakes decisions, like decisions that require high reliability. Like, so when we talk about high stakes decision, you know, the power networks or like, you know, cloud service providers, which are required to provide high reliability, like these are critical infrastructures which are required to be functioning all the time, but we cannot ensure that they function all the time, but at least we want to ensure that they function with high probability. And typically when we are faced with problems like this, they get kind of like encoded in a simple abstract framework called probabilistic constraint optimization or chance constraint optimization. Like, so what you have here is you want to minimize the cost subject to some probability of some adverse event kind of being controlled, or in other words, probability of some whatever you want to happening with very high probability. So you want to ensure the probability of something desirable happens with high probability, or alternate conversely, the probability of some adverse event happening with low probability. So this gets called as chance constraint optimization or chance constraint programs, and this remains the go-to. Like, so in numerous applications broadly in engineering as well as in operations research, like power systems, electricity markets, cloud server provisioning, several settings, emergency medical provisioning, disaster relief planning. When the stakes are high, decisions kind of, and when the decision making at scale, large scale, it gets done via writing a formulation like this, and it's called chance constraint formulation. And just to ground the talk in a couple of concrete examples, what I have here is like, you know, the first question is on the disaster relief response. How would you locate and resource outposts, relief outposts and relief passages, such that, you know, like how do you resource them such that, you know, in the event of a disaster, in the aftermath of a disaster, the shortfall of critical supplies can be prevented with a high probability. A very natural question, you want to ensure such a thing happens with, you know, the shortfall is prevented with high probability. And when faced with a setup like this, and if this is a really large scale network with 1000 nodes and stuff, then it's natural to write a formulation like this, where you kind of minimize the cost subject to ensuring that, you know, there exists a flow in the network, you kind of resource the nodes sufficiently so that there is a flow in the network which meets the demand with high probability. Or like think about, like, you know, the soccer World Cup coming up, or like the cricket World Cup in 2027. So these are kind of hosted in cloud servers, and these are demanding events to provision, because you are catering, you know, to a large number of concurrent users at scale at the same time simultaneously. So this is an example, like, kind of, you know, of how AWS went about, like the challenge, describing the AWS challenge, the Amazon Web Service, for hosting Super Bowl, a similar event, like similar sporting event on American football, where you kind of have to handle such large scale events. These are business critical, and you kind of like are handling a large number of concurrent users. And when faced with problems like these as well, you may as well like kind of think about, you know, you want to provision enough reserve capacity as well as enough servers such that the shortfall or like a disruption, a customer disruption is not experienced with high probability. It gets written like a formulation like this. So these type of chance constraint formulations remain the to go for like handling such high reliability. So in the morning talk, Vineet was mentioning about the service level agreement. So typically when hosting a sporting event like this, like the broadcaster enters into a service level agreement with AWS, saying, hey, I don't want like more than 99 point. I don't want more than 2% or 0.5% of the customers to be experiencing disruption simultaneously at the same time. So this kind of like this remains, despite this being a non-convex problem and computationally being very challenging to solve, this remains the go-to because of this pleasing, intuitively pleasing way of formulating, which is it's a conducive for modeling service level agreements, contractual agreements, and so on. Anyway, when it comes to the literature, it's indeed quite rich. The topic of chance constraints has been around since like 80s or 70s. So the early papers, like in 60s, the early papers kind of like focus primarily on computability. Like when are these chance constraint problems solvable, and particularly under what assumptions? If I have Gaussian, is it solvable? Or under what conditions? If I have long concave distributions, is it solvable? So the early stream of literature in the before 2000s like focused primarily on computability leveraging convexity. After 2000s, like maybe like one more stream emerged which said like hey, what, like we cannot be relying on convexity all the time. Can I have efficient approximation procedures? Like one is this so-called scenario approximation, another is sample average approximation, sorry, another is basically a kind of having a CVAR type relaxation, convex relaxation to the chance constraint and seeing how well it is performing. Or like you introduce cuts like which strengthen the MIP formulations in chance constraints. So a very, very rich literature on how to kind of approximate the problem. Again, computational focus. And the third one is the third stream says, hey, these are anyway hard problems computationally, and I don't know the underlying probability distribution. So why not let me, let me kind of like formulate the model in a different way so that some tractability is kind of obtained. And this is the third stream which kind of like studies how to get tractable chance constraint formulations. If you have probability constraints, they are nasty non-convex constraints to handle. So if you are having them, how to kind of get tractability despite the non-convexity, there is a rich literature again. This is not fully representative. It's kind of like, it's a very rich literature, but a small snapshot. Now, this talk is, despite this rich literature, this talk was triggered by a simple question which David Goldberg was asking a few years ago. He was asking, hey, what, you guys have been studying rare events and large deviation stuff. So, can you answer this simple question? Like, if I kind of like, if in the event of a sporting event like Super Bowl or Soccer World Cup, if a broadcaster wants to kind of like, raise their reliability target, like, raise their goal by, I want the customers to be, not experiencing disruption by a fraction, like from 5%, I want to raise it to 2.5%. Can you say how much the costs will grow? How much the contract price should go for changing the reliability target like this? Or if I have a 25% increased capex, how much more reliability can I offer? Can you answer questions like these, like intuitive questions like this? Despite this rich literature, to the best of our knowledge, we kind of have not been able to kind of find answer to these questions. So the first question that we are asking is, for example, if the broadcaster wants to have the fraction of customers experiencing disruption, how much should the cost grow? How much should the resource allocations grow? A very intuitive question. Qualitatively can we understand? In other words, what do I mean? To be a little more precise, so if I kind of look at the target reliability in the x-axis, and if I look at the costs for attaining the reliability in the y-axis, how should this cost grow as a function of alpha? A very simple question. How should the cost scale? That is the first question that we are asking. And examples, we can keep asking more questions, more structural questions like this. Instead of being primarily methodological, here the question is like to gain an asymptotic understanding and use it for guiding statistical learning. So to meet a 5% larger viewer base, how much should the resource allocations grow? Or with the 25% larger capex, how much can I kind of improve the service level? So this type of question. Now, to be kind of a little more precise, the question that we are going to first consider in this talk is the following. Can we sharply characterize how the optimal resource allocations? It's very clear. If you are raising the reliability target, the resource allocations should grow. But how fast should they grow, and how should the accompanying cost scale so that you can maintain the high reliability target? That is the first question. Yeah.
Do the eventual providers
let's say in this case, like a streaming provider, they are provisioning bandwidth from some vendor, right?
Yes.
So, as you get more and more stricter SLAs of the streaming provider with the bandwidth vendor, yes. Do costs go up as you get stricter?
Yes, certainly. Like exactly, the costs grow up, and how should they grow up is in terms of the underlying problem primitives is what we are trying to understand here. Yeah, that's the first part of the work. The first fundamental question is like how should the optimal resource allocations and cost scale to meet the high reliability requirements. And the second question is, an often overlooked question is, if I kind of, a lot of effort in the chance constraint has been primarily about like given a probability model, how can I formulate, how can I kind of solve the problem, how can I kind of solve the problem methodological. But if I look at the pipeline, like typically I'm not given a probability distribution to begin with, like so there are hundreds of uncertain variables in the problem, and only typically data is present. So if I look at the pipeline from data to decisions, how to perform learning under high reliability constraints, that is the second question. So that is also something that we hope to address with this in this paper. Okay. So the question 2, how to learn under high reliability constraints. One of the most basic example of the chance constraints is the quantile estimation. Like so, if you kind of think about quantile estimation, it can be written like this. So one of the basic elementary, the most elementary example of chance constraints is the quantile estimation. And when I talk about quantile estimation, it probably should kind of trigger something in your mind, like which is like, you know, quantile estimations, estimating quantiles can be easier if you are talking about, you know, median or like, you know, 75 percentile. But if I am talking about 99 percentile or more, the estimate of the quantile can be harder. So the same problem manifests here too. You look at this example. Let's say you are given 3 years of daily demand data, and you want to find an optimal allocation of node generation capacity such that the probability of network disruption is less than 1 in 1,000. So you're given 3 years of data, which is what is representative of what is happening today, and you want to find a probability of network disruption which is less than 1 in 1,000. So what is the challenge here? The challenge is, if you want, you are not even going to see one sample representing the network disruption with this type of data sets. Right? So if you, because 3 years of data is about 1,000 data points, about 900 data points, roughly about 1,000 data points. So you are probably going to see one or like not even one sample representing the network disruption in this with this such a data set. If I'm not going to see samples, then how am I going to ensure even feasibility? Forget about optimality. Like how can I even, like even if Oracle comes and gives me a decision, I cannot even verify feasibility if I don't have enough samples. So that is the difficult part. And let's see how it manifests in experiments. So one of the easiest ways in which these chance constraints are solved is by the so-called sample average approximation. So what is happening here is you have the probability constraint, you have a number of constraints you want to satisfy with high probability, and what you do is you kind of like, since you don't know the distribution, you replace it by the sample average. You replace it by the sample average, and when you have the sample average, and you solve the resulting sample average approximation. So you replace the probability constraint by the sample average and you solve the resulting optimization formulation. This is what is done typically, and let's see how it performs. So here in the x-axis what I have is I want to, that the target reliability level I want to ensure, and in the y-axis what I have is the delivered reliability. So for smaller levels of reliability, let's say if you are targeting 90% reliability and if you have 1,000 samples, you are able to offer, you are able to meet it, no issue. If you are looking at 95%, okay. But if you are looking at 99%, it starts to taper off, and it tapers off, it tapers off, it tapers off. It never like kind of improves beyond a point. Just because, you know, there is an aura of like, you know, safety. There is an aura of safety. There is a false aura of safety because the sample average approximation believes decisions to be safe, which are not truly safe because it is not experiencing any network disruption at all. It is not seeing any disruption event at all. And that's what is seeing as a tapering here.
So this is saying if you use the sample average approximation,
yes,
then the target delivered reliability tapers off.
Yeah, it tapers off. If you use the sample average approximation, the delivered reliability tapers off.
I see.
While even if as you are asking for more and more reliability, but the delivered reliability tapers off because you know the formulation is believing these decisions to be safe while they are not really safe.
So it's like the tails of the distribution is not able to
you don't see
not
them.
captured.
Exactly. That is the hard problem essentially here. You don't see them.
Sorry, Karthik, in this graph, are there some underlying samples that are, is it a function of how many samples you have underlying? Or?
The x-axis is the target reliability you are trying to achieve, and the y-axis is the out of sample delivered reliability. Like, you know, you solve the, yeah, there are you sample and then you solve the sample problem.
Suppose I generate a few billion samples.
Yes.
Do you still have this curve? Or?
So this is not a computational problem. If you have only 1,000 samples, how can you sample a billion samples? No, this is a learning problem. You have to live with the number of samples that you have. This is not a...
This picture corresponds to a certain amount of samples.
1,000 samples. 1,000 samples. 1,000 samples. Yeah, 1,000 samples. The 1,000 samples, if you have 1,000 samples, you have 1,000 samples. You cannot improve beyond it. Right. That's the bottleneck.
So just to be clear, number of samples was fixed throughout this, and
same throughout.
Yeah, and there's no important sampling of sorts happening.
There is no important sampling. You cannot perform important sampling because you don't know the underlying distribution. If you know the underlying distribution, you could perhaps, but you don't know the underlying distribution.
Got it.
Can you somehow approximate the underlying distribution by looking at last year's software World Cup?
Let's see. No, we will kind of see something of that type. Yeah. So the same bottleneck manifests in this picture as well. If you see, this is the target reliability, and you are trying to improve the cost, and you are kind of seeing the cost, like, you know, of the offered decisions, and this is the frontier of Pareto optimal decisions. It's not clearly visible in this slide. Like this is the frontier of Pareto optimal decisions, and this is the realized decisions. They shrivel beyond a point. They never improve beyond a point. So if you are just relying on the empirically observed samples, they do not improve beyond a point, and this is a fundamental bottleneck that cannot be improved. So given n samples, estimation is conceivable only if your target reliability level is kind of, you know, the target tolerance level is more than 1/n. Otherwise, you cannot even conceive of like offering this. Now, so the next question that we are asking is, can we kind of overcome the estimation barrier that has been, these two estimation barriers that we are witnessing with the data? So this is the second question. So the first question is, can we crisply characterize how the optimal resource allocation should grow? Hopefully, you know, that behavior brings out a certain statistical regularity. And often we know in statistical learning, if you have an underlying regularity, it facilitates learning. So can we leverage that learning to kind of overcome this 1/n estimation barrier? That is the second question. These are the two questions that we are asking. Any questions or thoughts at this point? Okay, good. So to the first question, what we kind of like, the type of results that we derive are of the following nature. So we identify a rich class of non-parametric models. We don't say, hey, we can solve this problem for all probability distributions because the fundamental barrier is unimprovable, but we identify a rich class of probability distributions which most of the practitioners would be happy working with. For this rich class of probability densities, actually learning can be improved in beyond the fundamental barrier that I wanted to talk, that I kind of exhibited. And then we kind of first show the scaling. We first show, hey, the optimal resources scale in this particular way and the optimal cost scale in this particular way as you are cranking up the target reliability level. So that's the nature of the first set of results. And the second set of results is to actually use the regularity to exhibit a solution, which kind of like, you know, nearly Pareto optimal. Like, you know, we are kind of like, you know, we use the regularity to develop data-driven procedures which can closely approximate the Pareto optimal frontier. This is the Pareto optimal frontier of decisions. Like it can closely approximate the Pareto optimal frontier. Even you know, when you are asking for steep reliability levels like 99.9% or 99.99%, even when you are asking steep reliability levels just with 1,000 samples, it still can meet it. So that is the second one. And the nice thing about it is, you know, the procedure that we are proposing kind of like doesn't require you to estimate what is the difficult estimation tasks, such as, you know, estimating the tail parameter, estimating the distribution tail. You don't have to estimate any of those. Whatever is difficult to estimate, we don't estimate, just like still we can kind of get such good performances. That is the second part of the talk. And if hopefully if there is some time, which is unlikely, I'll kind of move to an application on, how can we use this type of scaling phenomena to delineate the effectiveness of the library of DRO models which are available. So Vineet was talking about DRO models in the morning. There is a zoo of DRO models available. So how can we say which one is effective for chance constraints and which ones are not? Like one can use this scaling to kind of like discriminate and classify the conservative formulations from not so conservative formulations. So how to do that is the second application, which if we have time, I will go to it. Okay. So now I have motivated the question, I have said what type of results we have. Next I will probably go into the details of like, what are the probability distributions for which we can kind of overcome the fundamental barrier. So now I am going to state the assumptions on the probability distribution, and when it comes to modeling probability distributions, typically like, particularly in this setting of, we kind of have either two approaches. One is assume everything, which means, you assume a model, you assume a distribution model like a Gaussian distribution model or a T distribution model, whatever comes to your mind as suitable. You assume a model and let the data decide only the parameters of the model. Like, in the Gaussian case, you learn only the mean and covariance. In the T distribution, you mean only the location scale parameter. You let the data learn only the parameters. That is the assume everything approach, which is the parametric approach. The other alternative is to assume nothing and let the data speak everything, right? Like, so which is the non-parametric approach, which is the sample average approximation. So you have this dichotomy. So with the parametric assume everything approach, you are basically, you can think of it as you are doing a gross data pooling. You are using all the data to inform only the parameters, right? And you are using the parameters to let the rest of the talking. On the other hand, if you do the assume nothing non-parametric approach, you kind of like, there is no data pooling happening, just only the samples falling in the constraint violation event or speaking for it. Nothing else is speaking about it. So there is no data pooling happening.
What do you mean by data pooling?
Data pooling is like kind of just, I'm just saying, are you using all the samples to help your learning, or are you using only a small fraction of the samples? That's what I mean by data pooling. It's a rough sense, it's unconventional. Sorry? You will use all the samples, but only these samples will kind of inform the constraint violation events, right? Like, so in the second one, only these samples will speak. The rest will not really contribute. Sorry? Yeah, they are, it's because it's rare in some sense, exactly. So in terms of, this one can go totally wrong if you have the parametric assumptions to be wrong. On the other hand, you are going to see considerable variance and you are going to underestimate the probability of constraint violation, which is what we were seeing before. So what is the type of data pooling that we can kind of think about in the setup? We first ask, hey, what do the data sets suggest, and what is the minimal structure which is shared by all common distribution models that we use in practice? If I go to the data sets, this is for example a French format data set, like I kind of construct three different portfolios and then see how the tail events happen in these data sets. And what I see in all these three panels is the blue samples kind of represent the 5% largest portfolio loss realizations, and the red samples kind of represent the 1% largest, even more tail scenarios. They are the 1% largest tail portfolio loss realizations. What we see is how a portfolio loss becomes high, kind of like, how the 1% realizations happen is kind of getting mirrored in the 5% as well. Like whenever there is an underlying regularity, how extreme events happen in the tail kind of gets mirrored earlier in the tail as well, and that's what is happening in these data sets. And in all the distribution models that we use in practice, Gaussian, T, Archimedean copula, Wien copula, whatever models that we use in factor models, hierarchical graphical models, whatnot, all the models that we use in practice, they have a certain regularity. They don't have kinks in the tails. They have a certain regularity. They are well behaved. So how events happen later in the tails can be predicted, can be understood from earlier in the tails as well. So that's what I'm kind of like seeing here. When you say what is the minimal structure common to all these distribution models, here I'm considering a simple setup where I have where I am talking about a certain loss, any loss. The loss itself is not important, but I'm asking how does the largest how does 1 in a 10 power minus 5 loss events, how do those realizations happen, and how do those 1 in 100 realizations manifest? This is what I'm 1 in 100 samples I'm plotting in blue, and 1 in a 10 power minus 5 samples I'm plotting in red. And I'm comparing across 3 models, and what is striking about these 3 pictures is that like how extreme events happen later in the tails get mirrored earlier in the tails as well. So a completely non-parametric approach fully ignores what is happening earlier in the tails, and it uses only the red samples.
So what data is this that's used to generate?
So these are samples. So the ones I showed before are from French Pharma library, but these are just like, I took a particular distribution. So this is a bivariate normal distribution. This is a bivariate normal copula with marginal distributions being exponential, this being viable, and this is bivariate normal copula with the underlying marginals being exponential. So
and
they are
all of them have the scale behavior.
All of them have different marginals, that's all.
No, but they exhibit the scaling behavior.
They exhibit the self-similarity behavior. So this is what I call as self-similarity. How extreme events happen later in the tails get mirrored by how it happens earlier in the tails as well.
Does this happen in the French Pharma dataset as well?
Yes, that's what I was showing in the previous picture. Yeah, it may not happen in all datasets, it may not happen in all problems, it may not happen with all distributions, but in most distributions that we use in practice, this type of regularity persists. Like, because at the end, the distributions have a finite representation power. Like they are not like arbitrary kinky.
So,
yeah, okay. So that we have explored this only with the French Pharma. We haven't conducted extensive empirical. Yeah, certainly. But the alternative is anyway. I'll be using one of those parametric models, and this structure is prevalent anywhere. But what other alternative have we got?
No, then if the practical data set doesn't have this property and all the popular distributions do, then all popular distributions are not the right one.
Yeah, fair enough. I agree with that.
So,
comment, yes.
So will you?
Is there something special about this data set?
So this is not from a data set. This is this.
French Pharma data set.
Yes.
Like how well your results hold in others.
It is one of the easiest available data sets, so we took it. We haven't demonstrated this in every possible data set, that is true, but we have verified its validity only for common probability models, like common distributions.
So will you now take parametric assumptions that represent the self-similarity structure in this previous French Pharma thing?
Sorry?
Are you going to look at the self-regularity, self-similarity structure in the French Pharma and take parametric models that replicate that?
So I am saying we have taken one practical data set where this is present, and I am also saying independently in all parametric models that we use typically, this property is present. That's the case I am
Sure.
making.
So you'll assume something like this?
Yeah, we will assume something like
Okay.
this. Yes, exactly. That is the assumption that we make on the probability distribution. So the type of assumption that we are going to make on the probability distribution is relatively mild. It's a non-parametric assumption. It doesn't it just poses a certain regularity. It says that your tails cannot be arbitrarily kinky. The problem is how can I even verify it? Because you're not going to see much of the tails in the data. That is the issue. So it just assumes that the tail is not arbitrarily kinky. Instead, it has certain regularly varying phenomenon. So what type of regularly varying phenomenon? Either the logarithm of the density is sufficiently regular or the density itself is sufficiently regular. What do I mean by sufficiently regular? So if you look at the logarithm of the density, it looks like a polynomial. Like it looks like a polynomial or richer than polynomial. Or if you look at the density itself, the probability density itself, the density itself is like polynomial-like and it looks sufficiently rich. So if you look at the multivariate normal distribution, for example, the easiest to understand, the logarithm of the density is a quadratic function, right? Like, so if you see, it satisfies this type of regularity assumption. It's a polynomial, it satisfies this type of regularity assumption that we have. It can be slightly richer than the polynomial. So, and that's what we see here, right? And in the heavy tail case, a representative example for the heavy tail case would be a T distribution. A T distribution looks like this. You look at the reciprocal of the density, that's a polynomial. So if you have polynomially growing or polynomially decaying tails, or if you have the logarithm of the density is polynomially growing, the hazard function is polynomially growing, then you have this regularity. The polynomial can be slightly richer. You can have a logarithm multiplying the polynomial, not a problem. Still it will be fine.
Do I need to know which of the two holds or either is fine?
Either is fine. So for the results, I don't need to know this holds or this holds. Yeah, I don't need to estimate the parameters, nothing.
Sorry, the slides are not I think the projector is not too clear. So that's phi and z by n to the power what? I can't see.
Yeah, so what we are saying is the density, you look at the density, that roughly grows polynomially. So there exists a gamma, right? Like there exists a growth rate n power gamma, and if you multiply the argument by n, what you see is like, you know, the rate can be bounded, and it is not just bounded, it converges to a limit. That is what is the regularity.
Yeah, no, my point is that's n to the power, like just not
n
just the
to
symbol.
the n raised to the power gamma,
and
where gamma is an arbitrary number.
Is the rate, right? Yeah,
is the rate, exactly. Is the rate of growth of the tails. Okay, so this is the regularity that we are requiring, and that's all. Like, you know, when you think of what type of shapes, what type of distributions can satisfy this assumption, for example, you know, all these are okay, you know, like the data set can be any of this, it's okay. Like if you assume a parametric form, you may not have this richness, but any of this is okay. It can be oblong or whatnot, but as you go deeper and deeper in the tails, what you see is, like, you know, how the behavior deeper in the tails is mirrored earlier in the tails as well. That is the only structural regularity that you need. Everything else is fine. The tails cannot be arbitrarily kinky. Only if you have this regularity, then we can overcome the bottleneck that I talked about. Again, as I mentioned before, almost several of the distributions that we use in practice satisfy this. Like, so it's a rich set of models which satisfy this assumption. And what does this give me? What does this give me? Like, if I have this structural assumption, what does it give me? It gives me a certain control on how extreme events happen. So particularly if you are talking about how a tail event is happening, and if you want to control its probability, it gives me a control on handling that. Let's see how. So this is by this idea called large deviations theory or large deviations principle. Let me just quickly illustrate how it works. So let's say you want to understand how what is the probability of this event, right? Let's say this is deep enough in the tails. Maybe from the picture it may not look like deep enough in the tails, but let's say you have this, and let's say I have this probability density. So what I can do, typical large deviations arguments work like this. So what you do is you divide, you kind of like compartmentalize this set into small balls, and you say what is the probability of falling within that ball. The probability of falling within each ball is given by this density function times the delta, right? Like, so the density function determines that. And if you add the probability, of all these balls, like, you know, what you are going to see is, you know, each balls may have different values, but if you add these exponential numbers, because the density has an exponent, so if you add all these exponent numbers, and when n goes to infinity, only the largest one dominates. This is the rough idea behind large deviations. Only the largest one dominates. Only the largest exponent dominates. So that shows up here as the smallest of the rate, like the smallest, since there is a negative, the smallest of the rates kind of like prevails, everything else dies away. So what you get as a product of this large deviations kind of understanding is that the way in which tail events happen can be kind of like given into a location shape decomposition. So what you see in this kind of result is a location shape decomposition. So this red part is kind of like is captured by the shape of the rare event set, and the blue part, the t power gamma, is characterized by how far you are from the origin. So if you are farther away, then this will be larger. The location part alone will change, the shape part will not change. That is the key structure that you get out of this regularity. So as you go deeper and deeper, still the regularity prevails, the same type of argument will go through, and you get a similar kind of exponent also for the rarer problem. So you can have a clear understanding of how the rarer problem is happening from the earlier problem. So that's what this regularity buys us. Any questions? So if you have this, then what can we do? So that's where, like, so with this type of, only equipped with this regularity, it's not a parametric assumption, we just assume the simple regularity, and when you are equipped with the regularity, you can actually crystal sharply characterize like how the optimal cost should scale and how the optimal resource allocation should scale. So that is our main result here. The optimal resource allocation scale as follows. It scales as a vector x star, which is kind of saying how much the resource allocation should be in each coordinate, times the certain rate for growing. The rate of growth is explicitly identifiable. The rate of growth is explicitly identifiable, right? So if you can characterize the optimal solutions, obviously you can characterize the optimal costs as well, and that's what we have in the top. So there is a precise rate in which you can attribute to how the resource allocation should grow and how the cost should grow when you have the regularity in the distributional assumptions that we have taken.
You don't know the gamma, right?
I don't know the gamma yet. I don't know the gamma yet. But at the moment, this is only a structural result. It exists. Like when there is a gamma, there is a result. For learning, I don't need to know the gamma.
Sure.
Okay, so this is just a result. It's a description of the underlying phenomena. Right now, what you see is how does this result come about? Let me just explain the proof idea in a couple of quick words. It's not difficult. So this is the original problem. You want to minimize the cost subject to some probability constraint. What you do is you rewrite the constraint in a way conducive for large deviations analysis. What we saw is the probability of constraint violation can be kind of written in this e power minus location scale decomposition, location shape decomposition. So you leverage this. So you kind of write it in terms of logarithm. You take logarithm on both sides and divide the right hand side. You get a constraint like this, right? You get a constraint like this, and you let the reliability level alpha, the reliability level 1 minus alpha, you crank it up to 1. You let alpha go to 0, 1 minus alpha increases to 1. What you get is the what you get is an approximate constraint, a limiting approximate constraint for this prelimit constraint, and the approximate constraint gets dictated by the location shape decomposition. And the location parameter clearly tells you how the cost should scale as a function of alpha. So that's how you get these results. So it's from an asymptotic analysis of this chance constraint program. You can get these by performing the perturbation analysis of optimization problems. You can get this.
Can you go through this again?
Yeah. So you have this chance constraint problem, which is the original. You have a probability constraint. What you do is, I know this probability is represented, like, as you take alpha to 0, as you are cranking up the reliability level, these are tail probabilities. They should admit this representation, the location shape representation.
Right.
So now I am rewriting the constraint in a form which is conducive for this location shape decomposition, which is this.
Okay.
Right now I am kind of just like, since you are applying log, you are and putting a minus, you are going to get this here.
Right.
The denominator stays the same, logarithm alpha. I see. Right. Now the location parameter should adjust itself to become log alpha, and that is the scaling that you are seeing in the slide.
I see.
Right. That is exactly the scaling which is coming in the slide. So this. Now you can ask a question, hey, can you find what this x star should be? Can you find it? Actually, these chance constraint problems are NP hard problems. If I can find this x star, then I'm kind of like solving them well, right? Like, so I cannot find x star, but I can still sharply characterize the rate at which they should grow.
It's NP hard even under regularly varying?
Yeah. These are extremely hard problems computationally. But as such, still, I can characterize the rate explicitly. Though I cannot identify the solutions per se immediately, but I can identify the rate and this regularity that you are seeing. What you are seeing is x alpha is nothing but some x star, a vector x star, a 100-dimensional vector possibly x star, times a scaling function. A vector scale. Each coordinate is going to scale according to that coordinate's rate, and that is what is captured by this term. So you sharply characterize the rate, and that's going to help us later. This regularity is going to help us with learning. Questions? More questions? Okay. Before going to the learning part, let me dwell on a couple of implications of this. So what do we have here is the resource allocations, the optimal resource allocations, and the costs must scale at a certain rate, which is given by, what is the rate? The rate is determined only by the marginal distributions. So what you see here is, Fi is the marginal distribution of the ith coordinate of the random vector. So Fi inverse is the quantile function, and you are looking at the largest of these quantile functions, and that this is going to determine the rate at which the resource allocations should scale. That's all, right? So the good news, what you probably can see is, hey, if this is the case, then the joint distributions are not really playing a role in how the cost should scale, how the resource allocation should scale. It is not playing a role. It's probably, the joint distribution is playing probably a role with x star, but it is not affecting the rate of growth. Right? The rate of growth is primarily dictated by the marginal distributions. So in other words, the implication is the price of misspecification, the price of misspecifying copulas is going to remain bounded even if you are kind of like, asking for higher and higher reliability levels. This is a good news because, it's never easy to estimate joint distributions easily. If you're talking about 100-dimensional random vectors, like, how can you estimate the joint distributions reliably? But what this result is saying is, hey, don't worry, the price of misspecifying a joint distribution doesn't grow as you are cranking up the reliability levels. That is one implication. And now, okay, now let me just kind of go and explain how exactly the rate comes about. What is the exponent that is appearing in the rate of growth? Let me explain that. Different problems may kind of spring different rates. For example, if you have right-hand side uncertainty, if you have constraints which are kind of represented by what is called as this RHS uncertainty, right-hand side uncertainty, what you have linear constraints with the uncertainty, the uncertain vector is psi appearing in the right-hand side. This is what is a right-hand side constraints. For example, if you are trying to resource such that you are going to meet a certain demand where demand is psi, that is when this type of structure comes about. And in this case, what you have is, let's say the constraint is represented by a polytope like this, then if you kind of like look at how, how should you scale to kind of, how does the safe set change when you are changing the resource allocations? If it scales homogeneously or if it scales nearly linearly, which is what is going to happen in this case, then the rate would, the R will be 1. So if you see, let me introduce the precise assumption. The constraint function, which is psi minus Tx, when you look at the random vector psi, it is scaled by T, and when you look at the decision x, that is also scaled by T. What you get is like, you recover the constraint function again, right? The constraint function converges to something regular when you are scaling the decisions linearly. Like, the decisions are scaling linearly, and the decision should scale linearly for you to recover the constraint function, and in that case, the rate of growth R here should be 1. Now let's look at another type of constraint. The another type of constraint is like LHS uncertainty, the left-hand side uncertainty, where like this occurs in portfolio optimization type of settings where you are trying to find the loadings in each asset, which kind of like ensures that the asset returns are greater than a desired level. So that's what you have, a constraint like this. Here the decision and the constraints are appearing multiplicatively. When the decisions and the constraint and the random variable are appearing multiplicatively, you will have to divide the decision by T to recover the constraint again. Previously, you had to multiply the decision by T. You had to, when you are scaling the randomness, you have to scale the decision as well to recover the constraint. On the other hand, here you have to divide the decision to recover the constraint, right? So in that setup, you have the exponent R to be -1.
So in this RHS uncertainty, the limit should be xi minus AX, right?
AX, yeah, sorry, AX.
Yeah,
like
yeah,
okay. That's a typo. Thank you. This should be xi minus AX, and here it is just like again B minus X naught minus
that's
X,
fine.
suppose. Yeah. So and what you have is in this case R is -1. So in this case the resource allocation should not grow, but they should rather decay. The weights allocated to assets should rather, risky assets should rather decay. So that's what the R can be growing or R can be decaying. R can be positive or R can be negative. The rate can be, the resource allocations can be growing or they can be decaying. Or you can have mixed uncertainty, like you could have uncertainty in the left hand side and the right hand side. In those cases you kind of see a subtlety, some of the coordinates will have to be growing up and some of the coordinates will have to kind of like stay put, they have to grow down, and that's what you kind of see. Some of them will stay put, some of them will go down, some of them will go up, and that's what you can see with the left hand side and right hand side kind of behavior. So the nature of the constraint function primarily dictates, besides the quantile function, the rate of the constraint function dictates what is the scaling for the resource allocations and the scaling for the optimal cost. So different problems may have different R, and that's all we need to know. The R for a problem, there is no learning needed for it. You have the constraints, you can find out what R is for a given problem. It's not a hard task. Any question? So regardless of, the result is abstract, but you can contextualize it to different problems, and different problems may have different So the G function is the constraint function. In this case, the G function is psi minus AX minus B is the G function. Psi minus AX minus B is the G function, and this is what you get. This should also be A, that's a typo. Okay. This second implication. So now, previously I asked the question, if I can increase the capex by, if I can double the capex for this, for a particular project, then how much more higher service level guarantee can I get? I didn't have any idea before. Now, but with this type of scaling result, what I can say is, hey, let's say my current capex is this, I increase it twice, then I can project it back to the x-axis and say, hey, the service reliability improves by this far. So you can answer structural questions like this pretty easily if you have if you have this rate of growth. Okay. Now let me move to the application, which is what I started the talk with, which is how can I overcome the estimation barrier. So if you have only limited samples, if you have 1000 samples, like the performance shrivels beyond a point, how can I improve? How can I overcome this estimation barrier? That is the second question. How much more time do I have? 5. Okay, cool. Yeah, I'll finish with that. Okay, cool. Thanks. So, we have been looking at chance constraint problem like this. And given a level 1 minus alpha, you want to know what is the optimal resource allocation and what is the optimal cost. That's what we have seen until now. Now, let's say at the moment you have a decision which is good at the level 1 minus alpha. You want to increase the reliability level to 1 minus alpha prime, but you don't have the samples. What do you do? Let's say, you want to kind of like, learn it, you want to ensure a 99.9% reliability, but you have only at 99%. You don't have at 99.9%, neither do you have samples. You have samples for learning what is good under 99% reliability, but you don't have under 99.9% reliability. Now what do you do? Right? That is the question. Now, the question itself is perhaps ill-posed. Right, because when alpha prime times n, alpha prime is the target constraint violation level that you are willing to allow, n is the number of samples. When this itself is small, you are not even going to see enough samples. Even verifying feasibility is hard. Even if Oracle gives you an optimal solution, verifying feasibility is hard.
To check whether the chance constraints are satisfied, right?
Itself is hard, exactly. Even if I have an optimal solution, to certify it is indeed feasible itself is hard. Maybe the question itself is ill-posed. Should we be asking the question in a different way? And that is one of the important viewpoints which is coming from this. So we are going to twist the question. We are not going to ask the original question. Instead, what we are going to say is, hey, let's say, currently I am operating at this level of cost. Let's say I am willing to bear higher cost. Let's say I am willing to increase my budget or expenditure by a little bit or by a further amount. Then what is the service level that best service level I can offer? That is the question. You invert the question. Basically, you invert the question. Maybe this inverted question is easy. And actually, this inverted question is what is called as P model in the literature. This is what is a P model. You try to maximize the probability of constraint satisfaction, or you minimize the probability of constraint satisfaction subject to the cost being bounded. So this is the inverted question. Maybe the inverted question might be easier, right? So this inverted question is what is called as P model. Actually, in the initial paper of on chance constraint by Chance and Cooper, they kind of like posed multiple models. One is the chance constraint model, another is P model, another is E model. They posed multiple models, but somehow chance constraint kind of picked up. This alternative remains used here and there. Yeah.
So verifying is the same, right? Even here, we can't verify.
The guarantee. Okay, let me kind of say the verifying feasibility is easy, at least immediate. On the other hand, what I'm saying is, hey, this is my budget. I'm kind of like, say, I have $200 million more. I have to kind of do the best with what I have. Then, I'm trying to find an optimal solution, which kind of like but I'm not saying, hey, your probability of a violation even happening is less than 0.1%. I'm not guaranteeing that at all. I'm never guaranteeing. I'm trying to be the best with the resources I have. This is the inverted question.
But this problem will have an objective value.
Yeah, which is harder to estimate. I agree. This I agree. The same statistical difficulty persists, but the problem, at least verifying feasibility, is easy.
So this is the dual of that sort of.
This is just the inverted problem. This wouldn't be the dual. This is just like, I'm asking it. This is a different question actually. It's just the inverted question. Okay. The dual would be different.
So okay. So.
Yes.
Then I can solve this problem.
Yes.
Right? And somehow, if I know the solution, then I kind of know the solution is smaller alpha.
Yes, but I cannot verify the feasibility even. That is the problem.
Yeah, but approximately you can.
Approximately, when it comes to feasibility, there is no approximation. Like, when you are saying, hey, I am offering, 0.1% constraint violation, it will not exit beyond that, it will not exit beyond that, right? That type of guarantee is never possible to obtain. In other words, I cannot go out and say the type of solutions that I am kind of going to create satisfy or kind of like, optimal for this problem, I can never go and say. On the other hand, for this inverted model, I can say. So here is what, the solution is simple. We had a structural result. We had a structural result which said, the chance constraint solutions exhibit a scaling. They are basically an x star times a scaling function. Basically, I am going to extrapolate on the trajectory of the scaling function. So what I have is, I solve the problem at the level of reliability for the solutions I have, and I am going to extrapolate. I am going to consider an extrapolated parameter of, I am going to create an extrapolated trajectory, which I will show next. And that extrapolated trajectory is what I am exhibiting, and these are relatively large scale instances, not carefully selected, randomly selected instances, and what we see is that the extrapolated trajectory, because of the regularity, the extrapolated trajectory actually has a good, like it approximates the Pareto frontier very well. That is what we are seeing. This is the light tail case. You change the distribution, you kind of do a heavy tail case, still it continues to kind of like approximate the trajectory. The blue region is basically the set of all attainable solutions, a set of all cost and reliability pairs, and this frontier is the Pareto frontier, and you are very closely approximating the Pareto frontier. At least picture, it looks impressive. Now, what type of algorithm does it? It's a simple algorithm. It's easy to explain. Let's say I have a solution at this target reliability level because I have sufficient samples. Like this is, let's say, 95% reliability level, and I have sufficient samples for inferring at this reliability level. Then what I'm going to do is, now I have the structural regularity. I'm going to extrapolate along the structural regularity. How? Let's see. So I solve the problem at the base level, and then I kind of like say, find the solution. I look at the extrapolated trajectory and find the solution which attains the budget B. And that is going to be along the Pareto frontier. So that is a simple algorithm. It does not require the decision maker to perform any difficult estimation tasks. It doesn't require you to estimate any extreme value parameters, indices, or so on. It just kind of like, it's a simple extrapolation. As long as you know the R rate for the constraints, everything is going to go through. And the result kind of will say, this is an informal statement. The extrapolated trajectory is optimal for this P model, this so-called P model. It is optimal for this P model. It's optimal in solving this P model. In terms of empirical efficiency too, so what we see is like, we kind of like contrast with the baseline, which is the sample average approximation. We do see sample average approximation kind of like, as you kind of change the budget parameter, as you increase the budget, the problem becomes harder and harder because the solutions are going to become, the constraint violations are going to become rarer and rarer. But we continue to see impressive performances with the proposed extrapolation scheme. On the other hand, the sample average approximation does not improve beyond a point at all.
Are you using the gamma in the proposed scheme?
So I am not using the gamma.
Can you show that again?
Yeah, that's the good question. Yeah, I am not using the extreme value parameter anywhere.
What is in the power of TB?
So the power of TB is R. R is the scaling rate which is coming from the constraint function.
I see.
The constraint functions are known to you. It is a left-hand side constraint or it's a right-hand side constraint. It has quadratic constraint, but the rate of growth of constraint function is known to you.
I see.
Right? Each coordinate of the R is explicitly known to you, and you are just going to kind of like, consider an extrapolated trajectory based on this simple approach, and you are going to invert for the budget, given budget. And as the budget is increasing to infinity, this is going to be optimal for the P model. That's the type of optimality that you can show. But you can never show this type of thing is optimal for the original chance constraint model. So that's the difference I wanted to kind of show. Anyway, so I'll stop here perhaps. I'll just conclude quickly. The second application I will not get into. So as such, at a high level, we consider the problem of allocating resources under high reliability constraints. There is a large body which is focusing primarily on algorithmic aspects. But we kind of ask a slightly different question which diverges from that methodological questions. We instead ask, hey, what is the structural regularity in the solutions? Now, once you kind of like have a structural regularity, can you leverage it to improve your learning? So that is the second question that we exhibited. Hopefully, this is an example where my training was in probability, applied probability. But then optimization is also extremely appealing because you know whatever the problem is, you can write down the constraints, you can write down the objectives, and you can solve the problems at scale, right? So hopefully, this is an exhibition of like you know how when things are put together from different kind of like perspectives, something new can happen, right? Like so. The title of the workshop is explore probability optimization operations. Like hopefully it's an exhibition of that. Thank you for the opportunity. Thank you.
Practice, if you are somebody who's playing IPL final or the World Cup, can't you learn from some empirically, some historical data, budget for some increase? Usually it will always be an increase and
Yes. So the past data that we are using to learn the base solution is the historical data like that. So that we are learning a base solution, we are extrapolating from the base solution. That is learned from historical data like past ideas. Yes, exactly. Yeah.
Then you would typically form the Lagrangian of this problem, assuming the convexity of the problem, and then you could see how large the deviation is to study the difference in the bounds of the objective.
Yeah, possibly. But the trouble is, even with the statistical difficulty of approximating a wave probability remains regardless of whether it is in the constraint or it is in the objective or it is in the differential. Right? So that will be. Right? So that's what we could have done that as well. It would have been
Let's say you have 1,000 samples and you are working at the alpha equal to 0.01 level of whatever that is called. How do you know whether you have already entered the self-regularity? You can't do that.
But the other question is what option have
So as in if you don't know whether you have entered the self-regularity regime yet, extrapolating the trajectory will not be the right thing to do, right?
Will not be the right thing to do. I agree. But the alternative is inferior. That's my decision.
Yeah, but is there no way to figure out how to?
When you have low samples, doing any hypothesis testing will be pointless.
I see.
When you see nothing, and saying something itself like becomes hard.
I see.
To kind of conduct rigorous hypothesis testing, saying have we entered an asymptotic regime or not will be like
Okay, I see.
Certainly, I think you certainly can guarantee that. The only trouble we are kind of seeing with the complexity of it is still anything looks like compared to what happened. So you can have an extremely conservative kind of statistically satisfies that. So if you are trying kind of solve the transmission problem in a complex case, then the reserving bounds can be extremely conservative, and you could end up having extremely higher costs. And the second difficulty is convexity in multi-dimensions is easy to kind of postulate for days, but like multi-dimensional case, like if you go to 2 dimensions or even 100 dimensions doesn't matter. What does convexity even manifest in techniques are like infinity and for bounds reserving bounds becomes hard. These are the possibilities. Thank you.
So let's thank the speaker, and I'm sure there'll be more questions, but let's keep it offline. Yeah, I will. Yeah.
Hello, everyone. It is my great pleasure to welcome Professor Alexander Proutier. Professor Proutier joined KTH Royal Institute of Technology in 2011. Prior to this, he worked as a researcher at Microsoft Research and earlier as a research engineer at France Telecom R&D. He has also served as an invited lecturer and researcher in the computer science department at ENS Paris. He holds a PhD in applied mathematics from École Polytechnique. His research interests lie at the intersection of probability optimization and machine learning with a particular focus on applications to communication networks. His work has received wide recognition, including the ACM Sigmetrics Rising Star Award in 2009, as well as Best Paper Awards at Sigmetrics 2004-2010 and at MobiHawk 2009. He has also been the recipient of several major research grants such as ERC Consolidator Grant, VR Individual Grant, SSF ICT Platform Grant, and an SRA Grant. Please welcome.
Thank you. Can you remove the... Yeah. Okay, perfect. Thank you. All right. So thanks, everyone. Thank you, Sandeep, for the very kind invitation. I'm very happy to be here. Last year I could not make it. This year I'm very happy about coming back to India. I will talk about emergence of low-rank structure in reinforcement learning. This is a joint work with my postdoc Bastien Dubai and my PhD student Stefan Stojanovic. This is published at NeurIPS a few months ago. Let's see. Okay, so the underlying questions that we want to answer in this talk and that are kind of puzzling me right now is why are low-rank structure ubiquitous in modern machine learning? And what gains in sample efficiency do they enable? And of course, so as I said, I will treat this problem or address this problem for a very classical reinforcement learning task modeled by a Markov decision process. So we have a Markov decision process with transition probability P, a probability to move from state S to S prime given that you play an action A. You have a policy, which is a stochastic matrix. This is a probability of choosing an action A in state S for all S. And this policy typically induces a Markov chain in the space of state action pairs, and the transition matrix is denoted by P pi. Of interest, of course, in reinforcement learning or in dynamic programming in general is the Q function, or the state action value function of a policy. And so if you give yourself a reward function R, this Q function is just the discounted reward accumulated over time, given that you start in a state S and that you force yourself to play an action A. And this is a very important quantity that is present everywhere in all reinforcement learning algorithms. A very interesting quantity in reinforcement learning that is not known enough is the notion of successor measure, which is enabling reward-free reward. It's a discounted sum of the probability, the transition probabilities to the power of the time. And what is nice with this successor measure, which is a matrix in dimension SA square, is that if you give me a reward function and if I have access to the successor measure, by just multiplying on the right side by the reward function, which is a vector, I get the Q function. So if you learn M pi, you learn the Q function of the policy for any reward function. So that's very interesting.
What is P pi exactly? P pi is at time step P, the probability of subsequent action.
Which one?
What is P pi?
P pi. P pi is a probability that if you are in state S and that you play action A, that you move to action state S prime.
But
Sorry? P pi to the power t.
So no, but how do you compute it? Because that depends on the state, right? So
This is a matrix. This is a matrix. Yeah. So you multiply matrices. Yeah. Sorry, no worries. This is very good. All right. So what is important in RL to be aware is that if you want to estimate the Q function or the successor measure, which are matrices, right, in a sense, you need entry-wise guarantees. Why is that? Is that essentially typically algorithms like gradient, policy gradient methods, or all the algorithms that are based on policy improvement methods need to be greedy with respect to the Q function. If you want to be greedy with the Q function and have some guarantee, you need to have guarantee entry-wise on these matrices. This is very important in RL. Okay, so in most practical relevant RL algorithms that we use today, we use a low-rank structure as an assumption. It's imposed either on the transition probabilities, on the Q function, on the successor measure, whatever you say. So for example, you can assume that the Q function is approximate as a linear function approximation, which is a combination of scalar product of feature vectors and some weight. So the feature vectors could be given by the first layer of a neural network, and the weight is just the last layer, okay? So here you have, of course, a low-rank structure of size D at most, rank D at most. So this is the case for the DQN algorithm, which is one of the first algorithms to leverage deep learning in RL that dates back to 92, not 2015 by DeepMind. Anyway, so if you think that you have a low-rank structure, then the reinforcement learning often boils down to estimation of a low-rank matrix. And for estimation of a low-rank matrix, there is a huge literature, maybe starting by Candes and Recht, but I'm not so sure actually. Maybe there are other papers before that. Since we want entry-wise guarantees, there are a few papers that deals with that. This is a critical thing, and that's a beautiful story. There is a very nice analysis by Emmanuel Abbé and co-authors in 2020 that essentially gives guarantee with respect to the 2 to infinity norm, which in turn can lead to entry-wise guarantees. In my group, and I presented that last year online, you have a question?
Yeah, I have a question. Yeah, so assuming low rank in Q or P, is there some kind of equivalence between them? One implies the other, or?
Sorry?
Is there an equivalence between?
They are not equivalent. So if you have a low rank in transition matrices, then typically it's going to the Q function if you have a low rank reward function as well. But it doesn't matter. I mean, they are not equivalent. These structures are not really equivalent. They are different kinds of assumptions made by different papers, but what we question is the validity of this assumption, and we try to explain this assumption in this talk. So what I was saying is that last year I presented a paper here, and the paper tried to explain why when you do reinforcement learning, actually you estimate a low-rank matrix, but with Markovian data, so the entries are not independent, and that is a considerable burden. And then we managed to do that assuming that the matrix is low rank. Okay. So wait, so does it make sense to actually impose a low rank structure to start with? And the answer is no. So in general, the transition matrix induced by a policy or the successor measure are not approximately low rank. Even approximately, okay, in general. Well, so why we started this is that we thought, okay, maybe there is a sense of low rank when you try to think about it. So imagine that the Markov chain induced by a policy pi is irreducible and aperiodic. So it has an invariant measure nu, And we know, I don't know if it's Kolmogorov or whoever proved this, that p pi to the power t tends, as t goes to infinity, to a rank 1 matrix that essentially characterizes the invariant measure. So when t goes to infinity, then the dynamics kind of converge to a rank 1 matrix. Oh, that's interesting. On the other hand, you could say that, okay, the successor measure can be seen as an expectation of the transition matrix to the power of a random variable t that is actually geometrically distributed. This is the classical interpretation of the discount factor in reinforcement learning. So when gamma is approximately 1, you see that this goes to infinity, t goes to infinity, so you may think that you have approximately low rank successor measure. This reasoning is wrong, and I will try to explain a bit later. Okay, so, and also, this intuition is nice, but when you learn, you don't want to wait for mixing to happen. So this is a mixing phenomenon, right? I mean, I wait for the Markov chain to converge to its stationary regime, and then I have a rank 1 matrix. So in reinforcement learning, we want to learn without mixing, typically, because mixing time can be very large. And so we would like to understand when this matrix become actually low rank, maybe not rank 1, but we want it to happen much before mixing time.
Why is there an expectation of the probability that it's deterministic?
No, t is random. Yeah. Okay, so the problem statement now is how can we formalize a notion of intermediate mixing that would lead to the low rank of the transition probability or the successor measure to the power something, and without even the notion of rank, because the notion of rank, we want approximately low rank. We don't want to make any assumption. And the second question is, can one quantify a power pt of a stochastic matrix is well approximated by a low rank matrix? Okay, so that's the same question, but how can we exploit this property on the successor measure with entry-wise guarantee to actually boost the statistical efficiency of your algorithm if you want to do reinforcement learning?
Sorry, we are assuming P of pi is not low rank?
Nothing is, no assumption, zero assumption.
But if it is low rank, then things are okay, right?
What is low rank?
If the P of pi, the transition, one-step transition matrix.
If it's low rank, yeah, it works from scratch, but it's wrong. Typically, the dynamical systems are not low rank because dynamical systems are kind of driven by some kind of, let's say, think of an ODE. There is a very likely chance that you don't move too much. When you don't move too much, it means that the transition probability has a kind of a identity matrix embedded in it. And in this case, it's not low rank. So it's never low rank. I never saw a low rank matrix of a Markov chain. That's what we, yeah. Okay. So before starting, I will just introduce a few norms. So given a policy pi and a probability mu, measure mu on the state, we can define a probability nu of SA that is essentially the probability to be in state S and to apply action A under the policy pi. And then all the norms that we are going to consider, and this is just for convenience, are kind of built on the product, on the scalar product weighted by nu. Okay, but don't worry about that. This is not very important. But make sure that everything that we do, including SVDs, are kind of weighted by this kind of measure nu. And the measure nu could be related to the way we sample the data, or it could be related to the invariant measure of the underlying Markov chain.
What is the space X in our context?
X here is the pair SA. Yeah? Okay, so you recover the normal SVD when the new measure is uniform, etc., etc. A very important norm when you work with RL is a 2 to infinity norm, because it will lead to entry-wise guarantee when you estimate, when you do statistics. And this is the maximum over rows of the matrix of the L2 norm of lines, of the row. Okay. So with this definition, the 2 to infinity norm of identity is typically nu means inverse, that is typically bigger than n, okay? And the norm 2 to infinity norm of p to the power t tends to 1 if essentially nu is the invariant measure. But that's, I'm not going to tell you exactly why. This is a bit complex, okay? All right, so I said we don't want to take the rank into the picture because the rank is too precise. It's too boring to assume the rank is smaller than something. So we will need a substitute for the notion of rank. And our substitute is the 2 to infinity norm and a quantity that we call spectral recoverability, that is essentially an appropriate notion when you want to have entry-wise guarantee. So if you take a matrix n by n and you do its SVD, the spectral recoverability of M is just the max over rows of this sum of weighted singular vectors, where sigma I is a singular value.
What does that mean? What is spectral recoverability?
Yeah, well, it's appearing in the analysis when you do the estimation error analysis, and it is typically something that is similar to the coherence of the matrix, if you are aware of what it is. It's a very similar notion. Sorry, the coherence. Yeah. Okay, so this lemma is kind of, it tells you why it's a good thing, is that if you approximate the matrix M by its first singular vector, let's say, if you do a truncated SVD and you look at the error in 2 to infinity, then this error is bounded, upper bounded by the singular values and the recoverability, the spectral recoverability of the matrix. So it's a measure really of approximate low rankness. It's, we will see, related to mixing, local mixing even. And this lemma is a generalization of, maybe if you are familiar with Chatterjee's papers on low rank estimation, it's inspired by what he called the key lemma, that is kind of looking at the approximation of the low rank matrix as a function of the nuclear norm. Okay. All right.
The Chatterjee's result is with respect to the Frobenius norm?
Absolutely.
I see.
Yeah.
In the 2 infinite norm case that we have here, is it also that the R SVD rank approximation is the best approximation, or does that just say it's a good approximation?
No, I didn't answer your question.
Usually in SVD, if you take the top R singular value, it's the best rank R approximation to the matrix.
Ah, yeah.
So is that also true that this is the best, or rather you just have it's a good approximation?
I don't know. I know that if you bound this guy and this guy, the spectral recoverability, you have a good approximation. Okay. And that's enough for me. Okay, so now comes the questions of, yes, the successor measure is not low rank. So the idea is that you have to apply is to shift it by some integer k. So you introduce the shifted successor measure m pi k as a product of m pi times p pi to the power k. So what do you do? Essentially what you do is that you remove the k first step, or you average over them, assuming if you apply a reward function on this, that you gather no reward on the k first step. When you think about it, it's a good thing, because typically in reinforcement learning, let's say goal-oriented reinforcement learning, you want to go from the airport to the hotel, and your routing policy generally it's not converging, it's not getting reward after, let's say, a few minutes. Okay, you need maybe 2 hours to go there. So when the reward is far away from the initial state, then it makes absolutely sense that you are kind of approximating very well, or actually it's exact, the successor measure. Ah, that's another question. Okay. Okay. So I promised to explain why MemPy was not low rank. The successor measure itself is not low rank, and you have kind of, you can upper bound and lower bound the singular values of the shifted successor measure by that of the matrix p pi to the power k, and even if k is equal to 0. So as a consequence, the 2 to infinity norm of m pi is bigger than square root of n. Okay, so it's not small. We would like to have O of 1, but it's not the case. There is absolutely no chance that the successor measure is low rank in the sense that we want. On the other hand, the shifted measure, successor measure, will essentially depend on the Frobenius norm on p to the power k, and this could be well controlled. Okay, here is just an example, numerical example on a maze where you have a uniform random walk, for example. And here we plot, for example, the rank R error of the approximation of the successor measure shifted by k. And you see that if k is equal to 0, the error is big. Actually, it's normalized by square root of n here. So n is the number of state action pair. Okay, so at 0, you have no chance to learn anything. If you will see that a bit later. But as k is increasing, sorry, you see that, wow, it's kind of the rank R approximation of the shifted successor measure is vanishing. And this is exactly what we want.
Isn't this equivalent to using the mixing of p pi?
Sorry? Where are you?
Here.
Ah, okay, sorry.
So you said ki the to infinity norm of the k shifted successor measure is bounded below by the Frobenius norm of p pi. What was it? Can you show that again? P pi k. Yeah. Mm-hmm. So aren't you using essentially the mixing of p pi?
No, there is no consideration on mixing here. You know, it's like
as p pi k, as k increases, it goes to the invariant measure. So aren't you essentially doing that?
No, there is no assumption here in this proposition. It's true for all matrices, for anything.
Okay.
Yeah, I mean, we will see the mixing problems later. Okay.
Why does MK having a large 2 infinity norm tell us about it not being low rank?
Yeah, well, essentially, you will see that later. But essentially, there is a strong connection, and you could have guessed, between the spectral recoverability and the 2 to infinity norm, actually. And you see, they share the similar expressions. There is a correlation. Why I insist a lot on the 2 to infinity norm is that this quantity has to be controlled when you have to have low estimation error, when you estimate the matrix. And this we will see in the next slide. Okay, so yes, if you want to estimate the shifted successor measure, what is the sample complexity? Imagine that you gather data of transition between state S, A, and S prime. You can construct from this just empirical estimator of the transition matrix, and then you can construct essentially an estimator of the successor measure shifted by k. And this result is the main result of our paper, is telling you how big is rank R approximation of this estimator to the true matrix in norm 2 to infinity. So of course, if we truncate to rank R matrix, we have the approximation error from the previous lemma that is corresponding to, that is a function of the R plus 1's singular value and the spectral recoverability of the matrix. Okay, that's the approximation error. But you do also an estimation error, and this estimation error is a bit complex, but it's the product of 3 terms. And these terms are here, and I explain where they come from in the proof. The first term, E1, is essentially 1 over ZSA. ZSA is the number of times, number of samples that you have for the state action pair SA. And this is controlling, this E1 controls the spectral norm, the error of the estimator of the transition matrix in spectral norm. The second term, E2, is just a way to go from the estimator of the transition matrix to the estimator of the shifted successor measure by this formula. So you see that you have gamma, you have k. So of course, in the second term, you have k and gamma. This is not a big issue. The very big issue is in the third term, where we can control the difference of estimation in entry-wise guarantee, or in 2 to infinity norm by applying, for example, the Leave-One-Out analysis of Abe et al. And this term E3, there is the 2 to infinity norm of m pi k and of its transpose, okay? So you see, and you have the spectral gap, okay? So you see that if you have this that was, let's say, square root of n, you would lose all the statistical benefit of trying to estimate a low-rank shifted successor measure.
Small question. So in E1, in the spectral norm, how does the log show up? What's the intuition of the log showing up?
Okay. The log comes from statistics. I mean, this is extremely classical. If you want to have guarantee with probability 1 minus delta, you pay a price log 1 over delta. And then there are also the dimension of the metrics that are important. Typically, NR is the dimension of the metrics that you try to estimate, because it's a rank R approximation that you try to estimate.
So is this because of some concentration bounds that you've used?
That's a concentration inequality, yes.
I see.
What is that gamma delta in the E3?
Sorry?
E3, what is gamma delta? Gamma delta.
This is a function of delta, typically log 1 over delta as well.
Okay.
Sorry, I don't even know. I should check, but... So what is kind of amazing with this theorem is that it's complete, in the sense that there is no assumption. There is no assumption whatsoever. There is no low-rank assumption. It's an offline estimator, meaning that data is generated independently of the policy that you are trying to estimate the successor measure of. It could be written for any measure nu, not necessarily the invariant measure of under pi. And as I said, if nu is invariant, then we have a very strict correspondence between spectral recoverability and 2 to infinity norm. Okay, but what's important to remember now is that if you are able to control the 2 to infinity norm of the shifted successor measure, and it's bounded, it's O of 1, then the sample complexity, this is a corollary of the theorem, would scale as S8 divided by epsilon square to have an error, an entry-wise error of epsilon. So if the 2 to infinity norm of this matrix is bounded, then we have all the benefit of low-rank approximation, because otherwise you would need S square A over epsilon square samples. And this is minimax optimal. This is optimal. You cannot do better than that.
Epsilon is the error you're fine with.
Sorry?
So epsilon is the loss error you're fine with.
Yeah. This is the target that you want to put here.
I see.
but entry-wise, not 2 to infinity.
So you've controlled the K-shifted measure.
Successor measure.
Successor measure.
Yeah.
You wanted to approximate the successor measure itself, right?
Yes,
so
yes.
when you go to that, maybe things will change?
Yeah, things will change. We have bounds, one respect to the other.
I see.
But I don't care too much, because for me, as soon as K is kind of reasonably small, and the time horizon to reach the goal is very big, I have no problem with this. Another interpretation is to say, okay, what I want to do in reinforcement learning is to reach a ball of size K around the goal, starting from my initial state, and that's good enough. So there is a connection of this shifted successor measure to hierarchical RL, and this is a very good interpretation. And I don't care about learning the
successor measure itself.
Yeah, the K first step. I think it's easy problem statistically and statistically. What did I say? Statistically and statistically? I don't know. Okay. All right, so the question now, we have shifted the problem after shifting the successor measure. We want to know how to control these 2 to infinity norm. Why can we control them? And the answer, our answer, is local mixing phenomenon. So we will try to derive upper bound of this 2 to infinity norm using concentration bounds like Poincaré's inequality. And so this is our generalized Poincaré's inequalities that we use. General Poincaré's inequalities are typically used to upper bound the mixing time of Markov chain. What we want to do is to use them to actually upper bound the time it takes for the 2 to infinity norm of the matrix to have low rank. Okay? All right, so if you take the Dirichlet form of the Markov chain, there is a famous, this theorem tells you that if you can upper bound, lower bound the Dirichlet by this quantity, lambda and c being constant, then you have you can control the 2 to infinity norm, to the power k to the transition matrix to the power k as a function of c and lambda. This is our result, yes, but this is a benign extension of Poincaré's type 2 inequalities, I say. Okay.
I've not seen this. Can you explain what the Dirichlet form is intuitively?
Sorry?
What does the Dirichlet form represent intuitively?
This is the Dirichlet form.
Yeah, but what does it mean?
Yeah, we can take that offline. Or
Okay.
I had a question.
Yeah. To be honest, I'm not so sure myself, so I am completely honest.
Alexander,
Yes.
I had a question.
Yes.
Hey, this.
Yes, sorry.
So, I'm trying to relate this to RL, as we briefly talked yesterday.
Yeah.
So, are we saying that what is happening is that when mixing happens, are you in some sense a little constrained in what you can explore in the action space?
No.
Like
no. Here I'm actually studying general Markov chains, and I say when I skip the k first step and I average over them, there is a low rank structure emerging naturally.
Yeah, but what does low rank in the action space translate to? It means there are fewer degrees of freedom to explore the action space?
If you want, yes. Yeah.
Right, in some sense?
Yeah, yes, absolutely. The successor measure of a policy.
So
there is no exploration here. Again, it's a single dynamical system. There is no RL yet.
No. You have figured out when the mixing ends, sort of.
No, there is no mixing yet. Again, sorry.
Okay.
We do pre-mixing stuff. Yeah.
No, I was just trying to say, are we going to, is the intuition that we're going to converge on the optimal thing faster now?
So so here, the successor measure, if you understand what it is, it tells you what is the Q function of a policy pi. what I'm saying is that to estimate this Q function and then improve the policy, it will take much less time, much less samples to do that. And then I can iterate faster, and overall the RL framework will take much less samples. That's what. Low rank is telling you can cut the dimension of the matrix to study. Yeah, okay. Okay, so this, what time is it? Yeah. This generalized Poincaré inequality is typically used when we use, when lambda is related to the second eigenvalue of the matrix, in which case it gives you an upper bound on the mixing time, okay? K, when K gets to infinity, you look at there's this term and you look at K and you look at the decrease rate of this exponential, and this gives you the mixing time. But what we do is that we can have a much general setting where actually we can control the 2 to infinity norm. We don't want to have a C that is small, but we can control, if you do the same reasoning with the R+1 gap, if you want, spectral gap, which is much bigger than the second spectral gap, then you don't converge to 0. You have a penalty, that is the 2 to infinity norm of the R, the matrix formed by the R singular value vectors, but the convergence rate is much faster. So this is exactly what we wanted.
So UR is like MRK, MKR?
UR is the matrix formed by the left eigenvector, singular vectors of the matrix.
R many. Right.
And so if the matrix has some coherence, you know that this is bounded. So O of 1. Okay, so that's what I'm saying. If the coherence of the matrix is bounded by constant, then applying a shift of this with this scaling is enough for you to have what we want, a low-rank matrix according to our definition that will enable fast estimation of the shifted successor measure. And K here is typically much smaller than the mixing time. An alternative way of doing this is to look at what we call local mixing. We can apply Poincaré's inequality locally as well for subset of the state. And you can do this, for example, imagine that you are trying to do reinforcement learning on a video games where you move from one room to another. Moving from room G2 to G4 may take a lot of time, but let's say the mixing time within a room is fast. So you can apply your Poincaré's inequality there, and you can show, for example, that essentially if you have 4 rooms and relatively fast mixing in the room, then rank K, rank 4 approximation of the successor measure would be good. This would give you a hint on how to choose K and the rank.
So the 4 is the number of rooms here, that is why the 4 appears here?
Yes, 4 is number of rooms.
Right.
But the decomposition of the state space is your choice. You can do whatever you like. Because these inequalities are really powerful. They work for any subset of state. Okay, so this is just to conclude. I won't take more of your time, but we did experiment and it worked pretty well, actually. So this is typically what people try to illustrate as a toy example to illustrate how RL is working on maze. So it's goal condition RL, so it means that you try to learn the policies that leads to all possible state in the maze. Of course, there is different policies there. So you see here, for example, the fact that what is it? Yeah, the successor measure shifted. This is the spectral properties of the shift depending on the shift. So with no shift, it's here, and with shift, let's say 17, it's dropping drastically. So you really have this low rankness as soon as you increase a little bit the shift. And from the sample efficiency perspective, let's see what, yeah, I don't have the right picture here, but so this is without shift, so you learn fast at the beginning, but you plateau, whereas when you apply a shift, then you can learn much better, actually. Okay, so conclusion, and then I hope I have some questions. We have several contributions here. Theoretical contribution. We prove and we explain how low-rank structures emerge in dynamical system, and the analysis has absolutely zero assumption. So we say that when you shift the dynamical system, it has inherently, there is inherently some kind of low-rank structure. And we have sample complexity bounds on estimation of the corresponding low rank, the corresponding matrices to apply to the shifted successor measure. And also we have a quantitative relation between low rank approximation of Markov chain and local mixing phenomena. So that's kind of a very nice picture, I think. From a practical perspective, this gives a lot of insight into hierarchical RL. So shift your objective for improved statistical efficiency. If you suddenly goes from RL, pure RL to hierarchical RL, you actually boost your statistical efficiency at the expense of not being good when you are close to the goal. And as I said in the first slide, for me, this is part of a broader research agenda. I'm interested in trying to understand what is the intrinsic dimensionality of the manifold where the data is when you do machine learning, and how can you learn this dimension, and how is it improving your statistical estimation or your learning process in general. And I will stop here. Thanks.
Yeah, I had one question. So these ideas are for general RL problems, right? We didn't really make any assumptions.
Yeah.
Like the intuition sure comes from if you have a 2-hour long RL episode, and sure the first 5-10 minutes might not give you much reward. But then even so what's the intuition for say shorter RL where you're playing maybe a short game with somebody which does not have long episodes? Why does shifting maybe help there?
In games?
Yeah, for example, yeah. I mean, you gave a driving example, right? Where maybe, sure, it's a 10-minute, first 10 minutes and 2 hours don't matter, but if you have short episodes, like if your RL MDP is short, what's the intuition of shifting helping maybe? I mean, I get the math, but then...
but the intuition is that, I don't know, there is some kind of magic, yes. I mean, there are two parameters in what I discussed. There is the rank approximation R, how good you want to describe the matrix, and there is the K, that is kind of the shift. And they are related, but it depends on the dynamical system, and you should kind of infer what you want. I think there are kind of parameters that are specific to the systems that you are trying to study, but it's difficult to get intuition except from the local mixing examples that I gave. And we are working on this, and it's kind of, I think it's a first paper, to be honest, but we have already a lot of things. Well, now we are trying to exploit it. We try to do hierarchical RL with this in a kind of automatic way to learn what is R and K and so on. But yeah.
So I have a few basic questions. What is hierarchical RL?
So hierarchical RL is kind of where you have, imagine that what you do is that you have two kinds of policy. You have a high-level policy and you have a low-level policy. So the high-level policy, if you are in state S, will tells you like that in K step, you want to be in a certain goal state G.
Right.
Given the reward. And then the low-level policy will tell you, how do I actually reach the goal G? And
I
you
see.
learn these two things
There's a
independently.
2 time step sort of.
2 time scale.
I see.
Yes,
I see.
absolutely.
Okay, one more question.
Or more if you like. I mean, it's like,
yeah. So you started with saying ki if I wanted to learn the Q function, I can learn that by the successor measure.
Yeah.
Then you talked about the case-shifted successor measure, which you are able to learn very well. But I don't understand how that transfers to learning the Q function.
The Q function is just the product of the successor measure times the reward function.
Right.
So if I give you the reward function and you estimated m pi, then you have the Q function.
No, but you are estimating m pi k, right?
No, yeah, okay.
So how do you estimate m? You're not estimating m pi with m pi
No,
k?
I'm not estimating the true Q function. I
Okay.
estimate the,
And this
the
is
Q
enough for-
function by truncating the reward, by removing all the k first reward.
I see.
Absolutely, yes.
I guess you don't have to. That is the point.
Yeah,
I
you
see.
don't have to, and we have results quantifying the difference between the two.
And I think the point is you find an optimal K for your problem, right? Might just be
K is typically relatively small, and if it's relatively small, the price to pay is very negligible because it's about learning K-step policies. Like you can do it very efficiently for the low-level policies, if you like.
Okay, thank you.
It does seem like you want to go back also sometimes, right?
Sorry?
It does seem like you want to go back as well to the original problem.
Yeah. That's why we are trying to translate this to hierarchical RL, because we want to also learn the low-level policy, the missing K bits, if you like. But to be honest, I mean, well, depending on the problem, already reaching, I mean, it's like reaching in a neighborhood of 500 meters from the hotel is good enough. I see the hotel and I walk there. Yeah.
So I had a question about like discovering the intrinsic dimensionality of the data. So in low rank adaptation, like we want to like discover like the optimal like low rank R matrix that helps us fine tune an existing model to some new data. So is there some work that like you're aware of or you're working on that helps us do like fine tuning using like low rank adaptation in a better fashion?
Yeah, so that's a question that we would like to answer. We have published a paper where we managed to find exactly, to have an algorithms to adapt R to the data in system identification in control theory. There are other cases where I know how to estimate R correctly. So for example, but not in dynamical systems. So I'm trying to have a collection of results like this where I can kind of find the exact R or dimension that I want to learn. And I find it okay, kind of fun to do, but yeah. Yes?
Parts of this resemble, at least superficially, this literature that started with autoregressive, vector autoregressive processes that don't have contractive leading matrices, and you take case steps to basically
Maybe, yeah.
contractive, sort of in the spirit of this iterated random functions, the flow. Is it related to that or not?
Probably, it's probably related, yes.
It's like this case step idea.
Yeah, maybe it's very related. I think that you understand that in RL it's a bit complex. You have entry-wise guarantee. You know, it's like putting things together is kind of hassle. I am not aware of this literature, but I would be very happy to find. Yeah. Absolutely. Yeah. No, but I would be happy to have some pointers because, of course, we missed a lot of relevant work. And it's difficult to have new ideas these days, right? Yeah.
If there are no more questions, oh, sure.
Yeah, I just want to ask a basic question, that is the intrinsic dimensionality of the data is really important if your approach is that low rank structure emerge in the dynamical system. For example, now there are many, I think some alternate approaches there, like local embedding and they don't try to find the they are, even if you don't know the dimensionality of the data manifold, so there you can approach it in a different way.
Yeah, that's interesting. I don't know about these methods. I am very, very familiar with reinforcement learning algorithm, and all of them leverage low rank structure. So it's important to kind of connect there, but for these problems, I would be happy to discuss with you, and you can teach me something. Sorry.
No, there is already literature in it, like local embedding. That approach
Okay.
we can further discuss.
Applications of this, what are you personally excited about applying this to? Thanks. What scenario or use cases?
I mean, RL in general. I mean, in robotics, you typically state-of-the-art methods imply some kind of hierarchical approach. Of course, combined with deep learning. So yes, I mean, this is kind of our explanation of the methods that works today, and they are also, this is also a method to tune these parameters. So that's kind of interesting.
Sorry, small question. So hierarchical ML is, RL is saying that you have different policies and then a policy to choose these policies.
Sorry?
So what exactly, how exactly does hierarchical RL work? I think I didn't understand it earlier.
So you have a high-level policy that essentially tells you, if you are in the US and you want to go to India, maybe you go through Europe. So it tells you go to Europe. That's the
Euro policy takes
high-level
over.
policy. And then low-level policy which tells you how do you go to Europe.
I
and
see,
then,
I see.
you know, it's like step-by-step solving the problem.
I see. So it's not like you understand that there may be 5 large types of states I can be in. I'll train a policy for each. Then there's a policy that acts like a router which says, okay, this is the policy you should choose maybe.
Yeah. I mean, hierarchical RL is just aggregating state, local neighboring state in one state, and then you have decreased the number of states, so sample efficiency is going to be improved, and then you learn this high-level policy quite fast compared to learning the optimal policy.
I see, I see.
And then you learn the small policy. This is the same thing if you like to, it's a 3 decomposition of the state space, kind of. So, and yeah.
Are there any more questions? All right, let's thank the speaker.
Thank you.
Thanks a lot. Yep. So we have sure. Hey.
We have.
Okay.
Don't forget this can be. Thank you.
So we can meet in 20 minutes? No, out here. There's one more talk. Huh? There's a small talk. Actually, one more. Huh? So we'll meet at 17:35. Here. There's one small talk, 15-20 minutes, and then we are off for the day.
a professor and area leader of operations management at the Indian School of Business in Hyderabad. He earned his PhD in operations research from Cornell University after completing an MS at MIT and a BTech from IIT Madras. His research focuses on pricing and revenue management, retail operations, assortment planning, and dynamic programming models. Prasumit.
Good evening, everybody. Can you hear me okay? Perfect. So thank you for sticking around, and thank you to the organizers for this opportunity. What I'll talk about today is how a retailer, a firm, can make tailored assortment decisions to customers who may seek to avoid variety. And this is joint work with a bunch of fantastic colleagues. I'll make this more precise later on, but basically variety seeking means that a customer would like to buy something different from what they purchased last time around. Right? So if you had a customer who's variety seeking and they purchased this strawberry flavored yogurt last time, they may want to purchase something different this time around. Variety avoidance means customers have a tendency to stick to the same kind of product. Right? Now, having said that, this is probably a bad example because the kind of settings we have in mind are more in the online space, e-commerce, for example. So here, this is an example taken from this paper, and it talks about this company, Chinese retailer Alibaba.com. And again, abstracting out many of the details, here you have a customer who uses the mobile app, goes to the seller's store, and here the seller shows them these different products. Right? So the kind of application we have in mind is more in the online space, e-commerce, where it is easier for a firm to identify the customer, who know who the customer is, what they have done in the past, and then also be able to put together this assortment on the fly so that you can make these decisions in pretty much real time. So this is kind of the use case that we have in mind. So before I talk about variety seeking, variety avoiding behavior, I'll briefly talk about assortment planning. Now there are experts in the room, but for the benefit of everybody, I'll just give some brief background here. And I don't think I'll go through all the slides, but at least give you a sense of what the problem is about. Right, so if you think about this basic assortment planning problem, it is a stylized model, it abstracts out many things. But the idea is that you have a firm, a retailer, who has a total of capital N products. Right? And the firm's decision is to figure out which of these N products to show to a given customer. So a customer comes in, looks at the offered products, and either decides to make a purchase or leave without making a purchase. Right, so in this setting, the customer buys at most one product. Right? They either buy one of the offered products or leave without making a purchase. Sales generate revenues. And so the question for the firm, the retailer, is which of these products do I show to this customer in order to maximize my expected revenues? Now, what's the trade-off here? Why not just go and show the customer all the products? Because different products have different margins for the retailer. Some are high margin products, others are low margin products. And at the same time, customers may also like these different products differently. So if you just go and show all the products, it is possible that the retailer, the customer, may go and buy a low margin product. So you may have to think more carefully about what is the right assortment, what is the right decision here. So that also leads me to the next point, in that how do customers choose? Right, so a key ingredient to this assortment optimization problem is the underlying customer choice model, which describes how customers behave. One thing I should clarify here is that in this assortment optimization setting, the prices are fixed, the margins are fixed. So the only question is, what products do I show? Right, so the price is not a lever, it's not a decision variable here. Now, when we come to choice models, there are many different choice models out there, but a standing assumption for the most part is that a customer's choice is governed by attributes of the features shown to the customer. So what might be attributes? Style, color, size, what have you, but only on the attributes of the products shown to the customer. So here what we ask is the question, if in addition to all of this, what if the customer's choice also depended on what they purchased last time around? So suppose this customer went and purchased this product last time around. If that affects their choice this time around, how does that change the assortment decisions? And how do these decisions compare to the case where the customer's choice was not dependent on past purchases?
Yeah, sorry. So are you also modeling different customers having different profiles, or are we assuming the same customer but just them having the history, like the purchase history?
Right, so here we are talking about personalized assortments. So it's the same customer that the firm interacts over multiple purchase occasions.
No, so like if you have multiple customers, and if you want to use this framework, you treat each customer individually. There's no joint.
Yeah,
I see.
right.
I see.
So that's the question, right? So if there is this nature to a customer choice, some form of history dependence, how does that change the assortment decisions? And when we talk about history dependence, there is something very specific we are talking about. There are other things one could consider. Here the angle we look at is variety seeking, variety avoidance, right? And there is a lot of work what people find is that both types of behavior exist, and it may also depend on the product category. Right, so for some types of products, customers tend to seek variety. For other types of products, customers tend to avoid variety. So this is what people have found. And again, there are different models in the literature to describe the customer behavior. What we use in this paper is this specific model, which comes from this 84 paper and later adapted by these authors. So what I want to emphasize is that this is not our contribution. Right? So this is from the literature. There is a lot of math here. Later in the day, won't go through any of that. Just give you some main highlights. So here I have this P of I comma J of S. So what is that? It is a probability that a customer who previously purchased product I will go and purchase product J this time around if capital S is the offered assortment. Right? So this is the probability that a customer who previously purchased product I, so I is the previous purchase, will go and purchase product J in the current purchase occasion, given that S is a set of products shown to the customer.
So history depends only on I.
Yes. So just a one step, immediate purchase, absolutely.
Can you explain the three effects?
I won't, because I'll just try to give you some intuition here. Good, so let me just clarify that I equal to 0 means no purchase. That the customer leaves without making a purchase. Thank you for that.
But why is that also equivalent to I not being in the assortment? Because it might be that this new assortment is similar to something I bought earlier, but that earlier thing is not in the current assortment.
Again, one thing I will say is that this is something people have proposed, and we're just borrowing off that. Now, let me just try to give you the main highlights, and then I can take some of the more detailed questions offline, perhaps. Again, given the limited time. So here, one observation is that this choice probability depends on I, which is a previous purchase. Something else to notice that there is this capital V sitting here. So think of that as a variety parameter. Think of it as a knob that I can turn to control the extent of variety seeking, variety avoiding behavior. And I will talk more about that. A third thing that this choice probability depends on is this theta J of S. So what is theta J of S? It is a choice probability under the multinomial logit model. So some of you may be familiar. It's a workhorse in the assortment optimization literature, which says that every product has a number called the attractiveness associated with it. So Uj is how attractive product J is to the customer. So if Uj is higher, it means the customer likes the product more. So under this multinomial logit model, theta J of S is the probability that a customer purchases product J when S is the offered assortment. So you can think of this more complex choice model as some sort of generalization of this multinomial logit model to account for variety seeking, variety avoidance. So talking more about this variety parameter V, it lies between -1 to +1. So if it lies to the left of 0, then it describes a case where the customer is variety avoiding. And the extreme case is V equal to -1, which means the customer will never purchase anything else. They will always go and purchase what they purchased last time around. So that is V equal to -1. If V is to the right of 0, it describes a situation where a customer is variety seeking. Right? And the extreme case is V equal to +1, where they will never go and purchase the same product around. Right? They will go and purchase something different. And V equal to 0 is interesting because it describes a situation where the customer is neutral towards variety, which means their previous purchases don't affect how they view the products this time around. And it can be verified that if v is equal to 0, this complicated expression reduces to this multinomial logit model. Right, so that's what I was saying, in that you can think of this model as being a generalization of this multinomial logit model to account for the customer's attitude towards variety.
So the same thing as I equal to 0.
I equal to 0 is different, right?
Theta GS is the multinomial.
Yes. So what I was saying is that if you substitute v equal to 0 in all of these expressions, Pij of s is going to be equal to theta g of s identically.
No, because the first condition also says I equal to 0 or I not in the set.
Yes.
So they are equivalent.
Yes, so that there, absolutely. So if those two cases hold, also yes, we assume the customer resets to the multinomial logit model. Good. All right, so and this is just a visual representation of the same thing. On the x-axis, I have the variety parameter. It varies from -1 to +1. On the y-axis, I have the choice probability. So if you look at this dotted green line, P of 2, 2, it describes the probability of a repeat purchase. What is the probability a customer who previously purchased product 2 will go and buy the same product this time around? Right, so again, we see that if v is equal to -1, extreme variety avoidance, repeat purchase is 1. That decreases as this variety parameter increases, and at v equal to +1, it goes to 0. v equal to +1 is extreme variety seeking. They will never go and buy 2 again. That's what it is. So, and again, I should emphasize that there's been work done to estimate the parameters of this model. So what do I mean by the parameters of the model? This variety parameter and these u's. So there are ways to estimate these numbers. That is not our focus here. Our view is that this estimation has been done. Given that we know this choice model, given that it has been estimated, the next step, figure out what products to show. That is the question that we are looking at. That is v equal to 0, right? So there are two different shapes. One is to the left of 0, which is variety avoiding, to the right of 0, variety seeking.
So does it mean the right hand side will be equal to 1?
Say that again, please.
The right end, okay, v equal to 1.
Yes.
The probability should match 1.
The probability of a repeat purchase goes to 0.
Yeah, no, I'm saying if you sum up the property.
But there is also the outside option. No, you're right. I mean, this includes all of them. So if you add up this plus this plus this, that will be equal to 1. Yes, that's right.
And this is, the parameters will be person plus product.
Person dependent. And yeah, product means in the sense that these UJs depend on the product. Absolutely. So this is the problem that we are looking at. What is the sequence of assortments to show to a customer who may have an attitude towards variety, right? So you're interacting with the same customer over time. What is the sequence of assortments? And these assortment decisions are linked together because what you show the customer this time around impacts what they purchase, which in turn impacts how they view these products the next time around, right? That's the idea. So I don't have too much more time. So we have an analytical model. There are results. Let me skip that and just let me show you one result, which is this one here. Yeah, this one here. Right, so here we have two rows. VA stands for variety avoidance. VS stands for variety seeking. Right, and this first column here, variety ignorant, refers to a case where the retailer is ignorant about the attitude of the customers towards variety. So the retailer mistakenly assumes that customers are variety neutral when in fact they have some attitude towards variety. Right? So what do we find? We find that the retailer leaves money on the table by ignoring this attitude towards variety. Right? So if you don't understand that customers have this attitude, you go and optimize assuming variety neutral behavior, you're leaving money on the table and the loss is greater for a variety seeking customer. The second column here, or the third column, the last one stands for a myopic retailer. So what does that mean? Here the retailer knows the customer's attitude towards variety, whether they are variety seeking, whether they are variety avoiding, but they are not looking at the long-term problem. They treat each interaction in a myopic fashion, not accounting for the fact that you will interact with the same customer down the line. Right, so here the results are different in that if you know that your customers avoid variety, but you're lazy in that you don't go and solve this infinite horizon or this multi-period problem, you leave a lot of money on the table. Here, not so much. Right, so here this seems to be more like a second order effect. So if you have a variety-seeking customer, you know that, then even if you don't solve this complicated multi-period problem, you still don't lose a whole lot. Yeah.
Is it because the universe is large? For the second
Yeah, I mean, kind of, yeah. And universe large, and also you can sort of recover in that you make a wrong decision, but because they jump around, you can sort of get back into a good state. In the other case, they are sticky, so if you go into a bad state, you continue there, kind of.
And each customer is constrained to have number of purchases, or they can make as many purchases?
In each occasion, at most one, but over time, yeah. Yes.
What is the connection between the time horizon you are looking at and the number of items that you can sell?
So here there is no specific, I think it's related to Vineet's. So what Vineet was asking is there a restriction on how many products they can buy in total? The answer is no. But each time they come to the retailer, they will buy at most once. So if there are T time periods, they will buy at most T products.
But when you got this number, I mean, I think this is a very important parameter, the ratio of the two, right? The time horizon you're looking at. And the
so this is for the infinite horizon problem that we have. So yeah, so we have a discount factor and yeah. Yeah, this is the money you're leaving on the table by not making the optimal decisions. So that's all I had. I'm happy to take more questions. And the paper is there on SSRN and Absolute. Sorry. I can stop. I'm happy. I can talk to you.
Thank you so much, Prof. Sumit. I guess questions we can do it later. And Prof. Sumit, we have this hamper also for you. The talks are over for the day, but at 6:30 we have a cultural event, just some song and dance at the Black Box Theatre. It's just the place where you had lunch earlier this day.
Yeah, after the culture event, we are heading to for the workshop dinner at Windham Hotel. So we will gather at 7:30 at gate number 1. All right.